It all started with a daring launch as a delicate spacecraft, crafted with immense precision and care, embarked on a journey that had never before been imagined. Voyager 2 was not just another spacecraft, it was humanity's very first ambassador to the distant outer planets. Silently and steadily, it traveled through the vastness of space, observing and exploring the farthest reaches of our solar system with a sense of quiet purpose. Its mission was extraordinary, to uncover the mysteries of distant worlds so alien and strange that their very existence was hard to grasp. As Voyager 2 ventured deeper into space, it encountered enormous gas giants and icy moons, revealing environments unlike anything we had ever dreamed of. The data it transmitted back to Earth revolutionized our understanding of these remote planets. We saw Jupiter's raging storms, immense and powerful, far beyond anything on our home planet. Saturn's stunning rings, graceful and intricate, mesmerized scientists and the public alike. At Neptune, Voyager 2 uncovered fierce winds racing faster than the speed of sound, a phenomenon that challenged previous ideas about planetary atmospheres. Yet, it was Voyager 2's brief encounter with Uranus, the most enigmatic and least explored of the gas giants, that delivered some of the most baffling secrets. Hidden within the planet's unusual magnetic field, its many moons, and its strange sideways tilt, Uranus revealed mysteries that continue to puzzle scientists even today. These findings opened new chapters in space exploration and kept the curiosity of researchers alive, urging humanity to keep looking outward into the unknown. Even though Voyager 2's mission ended many years ago, the discoveries it made continue to resonate through the questions scientists still seek to answer today. With the help of new technology and fresh ideas, we are uncovering more about these distant worlds, especially Uranus, revealing secrets that the Voyager spacecraft itself could never have imagined. Back in 1986, NASA's Voyager 2 spacecraft performed an incredible flyby of Uranus, marking a monumental moment in humanity's exploration of the outer solar system. For the first time, scientists had the opportunity to closely examine this distant and enigmatic planet. Uranus, with its striking blue-green color, faint rings, and unique tilt, spins in a way unlike any other planet, rotating almost on its side like a rolling ball. But beneath the breathtaking images and data collected during that historic encounter, some findings hinted that our understanding of Uranus, especially its magnetosphere, might need to be reconsidered. Voyager 2's journey to Uranus happened under unusual conditions. Just days before the spacecraft's arrival, a rare and powerful burst of solar wind, a fierce stream of charged particles emitted by the sun, struck the planet. This surge was so intense that it compressed Uranus's magnetic field to only a fraction of its usual size. Normally, solar wind flows steadily from the sun, shaping the magnetic environments of planets and creating protective shields known as magnetospheres. These magnetospheres act like guardians, protecting planets from harmful solar radiation. But this particular burst was so extreme that it shrank Uranus's magnetosphere to about 1/5 of its typical volume, which in turn affected the data Voyager 2 was able to collect. A recent study published in Nature Astronomy suggests that such intense solar wind events are quite rare, occurring only about 4% of the time. If Voyager 2 had arrived just a week earlier, it would have encountered a much larger magnetosphere, one more comparable to those of other giant planets like Jupiter, Saturn, and Neptune. This means that the data Voyager collected might not fully represent what Uranus's magnetosphere usually looks like. For a long time, scientists believed that Uranus's magnetosphere was unusually weak. They thought it had very low levels of plasma, a state of matter where atoms split into charged particles, and lacked the intense radiation belts seen around other planets with strong magnetic fields. Voyager data seemed to show that Uranus's magnetosphere was nearly empty of plasma, both from the solar wind and its moons, giving the impression of a barren magnetic environment. However, new research has changed this perspective. Scientists now believe that the solar wind may have actually been preventing plasma from accumulating in Uranus's magnetosphere during Voyager's flyby. This fresh understanding corrects the earlier idea that Uranus was almost devoid of plasma. By reanalyzing Voyager data with this new insight about solar wind strength, researchers now think Uranus's magnetosphere is more similar to those of other giant planets than previously thought. This shift in understanding has also shed new light on Uranus's moons, particularly Titania and Oberon. Earlier observations suggested these moons orbited outside Uranus's magnetosphere, but recent research indicates they might actually reside inside this protective magnetic bubble. This discovery is crucial because it affects how scientists view these moons, especially the possibility that they may harbor subsurface oceans beneath their icy surfaces. The potential for such hidden oceans has captured the interest of researchers as it opens new paths in the search for life beyond Earth, particularly in the cold, distant reaches of our solar system. Now let's dive deeper into what we know about solar wind. When charged particles from the sun collide with a planet's magnetic field, they exert pressure that can compress, stretch, or alter the shape of the planet's magnetosphere. This interaction is never static. It changes constantly due to factors like solar activity and the planet's distance from the sun. Planets with strong magnetic fields like Earth, Jupiter, and Saturn are especially influenced by solar wind. This wind helps create protective shields that keep harmful radiation from reaching the planet's surface. In this way, a magnetosphere functions like a defense system shaped by the planet's magnetic field to deflect and redirect charged particles away. However, magnetospheres are not invincible. Their size and strength depend heavily on the pressure of the solar wind, which fluctuates in both speed and density. For example, when Voyager 2 passed by Uranus in 1986, solar wind conditions were extreme, with dynamic pressure reaching its highest point. This dynamic pressure results from both the speed and density of the solar wind. Under normal circumstances, Uranus's magnetosphere extends roughly 22 to 25 times the planet's radius. But during Voyager's flyby, the boundary, known as the magnetopause, where magnetic pressure balances solar wind pressure, was pushed inward to just over 17 times Uranus's radius. As the solar wind's pressure increased in the days before the encounter, the magnetosphere shrank significantly. This compression didn't just affect the magnetosphere's outer boundary, it likely influenced the planet's radiation belts as well. Radiation belts are typically formed by plasma originating from the planet's atmosphere, moons, and the solar wind. But the powerful solar wind during Voyager's approach probably pushed plasma out of Uranus's magnetosphere, creating a gap and altering the usual behavior of its radiation belts. This led to an unexpected and intense belt of electron radiation that puzzled scientists for years, until recent research finally provided answers. When Voyager 2 flew by Uranus, it revealed surprising and puzzling features. The spacecraft's data showed that Uranus has a magnetic field that is not only tilted at an unusual angle, but also offset from the planet's center. This made its magnetosphere appear extremely distorted compared to those of other planets in our solar system. For a long time, this discovery led many scientists to believe that Uranus's magnetic environment was uniquely strange. Now, with new data and understanding, the picture is becoming clearer and more complex, offering exciting new directions for exploration and discovery in the far reaches of our solar system. However, more recent research suggests that the earlier understanding of Uranus's magnetic behavior may not capture the full picture. Scientists now recognize that the changes in the magnetosphere observed at Uranus are neither permanent nor simple. Instead, these shifts set off a chain of intricate processes. For instance, when solar wind pressure intensifies, it pushes hot plasma from Uranus's magnetotail into its inner magnetosphere. This phenomenon closely resembles what occurs on other giant planets, such as Saturn. When the solar wind compresses a planet's magnetic field, it can increase the intensity of certain types of radiation and cause shifts in the magnetic field itself. For Uranus, these solar wind-driven events lead to stronger electron radiation belts and change the plasma composition within its magnetosphere. Fascinatingly, this means that under specific circumstances, Uranus's magnetosphere behaves more like those of other giant planets such as Jupiter and Saturn. This updated understanding helps scientists better grasp how Uranus's magnetic environment functions and how it compares with the magnetospheres of other planets in our solar system. When a planet's magnetosphere gets compressed, it can cause radiation belts to become more charged, similar to what happens on Earth during geomagnetic storms. On Saturn, this compression clearly leads to an increase in electron radiation. A similar process on Uranus may explain the unexpected surge in electron activity within its radiation belts, even though the planet was once thought to have very little plasma. Moreover, this sudden rise in radiation during the compression events could trigger changes in Uranus's magnetotail dynamics, including a process known as magnetic reconnection. The magnetic reconnection, observed on planets like Earth and Saturn, can cause plasma to be ejected from the magnetotail and pushed into the inner magnetosphere. This would alter plasma density and radiation levels. On Saturn, such events have been linked to stronger radiation belts and more intense auroras. However, predicting the behavior of Uranus's magnetosphere during extreme solar wind events is challenging. While scientists have a solid grasp of how magnetospheres react to compression on other planets, Uranus's unique features complicate the picture. Its extreme axial tilt and oddly shaped magnetic field creates special magnetospheric patterns that differ from those on other planets. These unique conditions could explain why electron fluxes are stronger and why Uranus's radiation belts behave in unusual ways. Recently, researchers have revisited the behavior of Uranus's magnetosphere, the region around the planet shaped by its magnetic field. This new insight is important because it helps scientists evaluate how these magnetic conditions might affect the possibility of subsurface oceans on Uranus's moons. The outer moons Titania and Oberon have long intrigued scientists, especially regarding the possibility of hidden oceans beneath their icy surfaces. These moons orbit Uranus at distances of approximately 17 and 22 times the planet's radius, placing them in a unique position relative to Uranus's magnetic field. Moons closer to Uranus, such as Miranda, Ariel, and Umbriel, are more likely to have subsurface oceans detectable through magnetic induction. This happens because Uranus's magnetic field can induce electrical currents in the conductive layers of these moons, producing signals that researchers can measure. Titania and Oberon, however, present a more complex case. They orbit near or just beyond the magnetopause, the boundary marking the edge of Uranus's magnetic influence and the beginning of the solar wind's direct flow through space. Because of this, these moons are less affected by Uranus's magnetic field. Earlier studies even proposed that Titania and Oberon might spend large parts of their orbits outside Uranus's magnetosphere. If this is true, detecting subsurface oceans on these moons becomes very difficult. They would be exposed to the solar wind and the turbulent region called the magnetosheath, which would interfere with the magnetic signals needed to reveal hidden oceans beneath their icy crusts. However, recent data has introduced a surprising twist to our understanding of Uranus's moons. It now appears that Titania and Oberon, two of Uranus's largest moons, remain within the planet's magnetosphere for the majority of their orbits. This revelation significantly increases the possibility of detecting subsurface oceans beneath their icy surfaces, making the prospect more feasible than scientists had previously believed. The discovery opens thrilling new pathways for future research, promising to deepen our understanding of the enigmatic Uranian system. Simulations indicate that Titania has less than a 4% chance of crossing outside Uranus's magnetic boundary, while Oberon's probability is slightly higher, but still low, at around 1.3%. This data overturns prior assumptions, showing that both moons generally orbit inside Uranus's protective magnetic shield. This matters greatly because the magnetosphere's presence influences how we approach the search for hidden oceans beneath these moons. Being mostly shielded by Uranus's magnetosphere increases the likelihood of magnetic induction processes occurring inside Titania and Oberon. Magnetic induction is a key tool for detecting subsurface oceans, as it can reveal the presence of liquid water beneath thick ice layers by measuring variations in the magnetic field around the moons. This means that future missions equipped with magnetic sensors could have a better chance than ever before of confirming the existence of these hidden reservoirs. Furthermore, the fact that Titania and Oberon orbit inside the magnetosphere means they interact predominantly with plasma from Uranus itself, rather than the solar wind plasma that typically fills the space around other planets. This distinction is important because it reduces the interference in magnetic measurements caused by solar wind fluctuations, thereby improving the clarity and reliability of data collected during observations. Science is a constantly evolving journey, always refining previous knowledge and sometimes overturning long-held beliefs. The evolving understanding of Uranus's magnetosphere and its moons is a prime example of this process in action. To fully comprehend this distant world, we must return with more advanced technology and a renewed spirit of exploration. A future orbital mission to Uranus could provide continuous, high-resolution data, allowing scientists to study the planet, its moons, and its intricate ring system in far greater detail than ever before. As plans for such missions advance, understanding the precise positions of Titania and Oberon within Uranus's magnetic field becomes increasingly vital. Moreover, knowing how the solar wind interacts with Uranus's magnetosphere will be critical for planning spacecraft flight paths to maximize the collection of valuable data. Magnetic studies, which have already yielded groundbreaking results on other icy moons like Europa and Enceladus, can now be applied to Titania and Oberon with greater confidence. A mission dedicated to these moons could use magnetic sensors to probe their internal structures, searching for signs of liquid water beneath their frozen surfaces. Such a mission would fill significant gaps in our knowledge, enhancing our understanding of the outer solar system's most remote worlds. The future of exploration in this distant region is taking shape rapidly, with established space agencies and emerging powers alike prioritizing missions to Uranus and its moons. In 2022, NASA added an orbital mission and probe to Uranus to its priority list for the Planetary Science Survey spanning 2023 to 2033. This decision underscores the growing importance of studying ice giants, which have remained relatively unexplored compared to other planets. NASA's proposed mission, known by the acronym P+, Plasma Environment Radiation Structure and Evolution of the Uranian System, is scheduled for launch in February 2031, with an expected arrival at Uranus in 2043. The spacecraft will focus on investigating the planet's plasma environment, magnetic fields, and overall heliophysical context, offering invaluable insights into the processes that govern ice giants. In addition to these objectives, the mission will collect data on Uranus's atmosphere and its rings, promising a comprehensive view of this distant planet. The launch window extends from 2030 to 2034, allowing flexibility in mission planning. Meanwhile, China is also entering the arena with its Tian-4 mission, set to launch between 2030 and 2034. This mission, carried by a Long March 5 rocket, will send 2 spacecraft on separate journeys, one to explore Jupiter's moon Callisto, and the other to conduct a flyby of Uranus. Marking China's first foray into ice giant exploration, the mission will carry instruments designed to study Uranus's magnetosphere. Although the spacecraft will be smaller than NASA's, the mission will rely on a series of flybys to gain the momentum needed for its journey through the outer solar system. The legacy of the Voyager missions, which were instrumental in exploring the outer planets decades ago, has set the stage for this new era of discovery. The knowledge gained from those pioneering journeys provides the foundation upon which these ambitious future missions will build, advancing humanity's understanding of the distant and mysterious ice giants that dwell at the far reaches of our solar system. However, our true understanding of space is propelled by an endless curiosity and an insatiable spirit of exploration. As humanity continues to gaze toward the stars, the legacy left by previous missions serves as a sturdy foundation, pushing us onward to expand our knowledge of the vast universe. Far out in the endless expanse of space, amid countless stars and galaxies, there exists a faint whisper. A whisper from a distant star that has traveled across light years to reach us here on Earth. This is not a story from a science fiction novel, but a remarkable discovery in the cosmos, offering a glimpse into the ever-growing understanding we gain about the universe. Scientists, attentively listening to the silence of the cosmos, have picked up an intriguing radio signal originating from a star system not unlike our own. The star, called YZ Ceti, is located just 12 light-years away. But this signal is no ordinary noise. It carries within it a potential signature of a magnetic field similar to the protective shield that surrounds our own planet Earth. Let us embark on a journey, traveling across light years, to uncover the mysteries behind these radio signals from deep space and to explore the magnetic fields of distant worlds. In the vast, quiet expanse of the universe, radio signals are like whispers that traverse unimaginable distances. But what exactly are these signals, and how do they manage to cross such colossal stretches of space? The answers lie in the strange and fascinating phenomena of space itself. Radio signals are a type of electromagnetic wave, similar to light, X-rays, or microwaves. These waves come from a variety of sources, including distant stars, galaxies, and even human-made satellites and spacecraft. Traveling at the speed of light, they carry invaluable information across enormous cosmic distances. These signals help us understand the composition of stars, the presence of planets, and even provide clues about the origins of the universe. How do we capture these distant signals? The key lies in a technology known as radio astronomy. Radio telescopes like the Very Large Array in New Mexico or the now inactive Arecibo Observatory in Puerto Rico are specially designed to detect and study radio waves from space. These massive instruments act like cosmic ears, tuned to catch the faintest sounds from the farthest reaches of the universe. Once a radio signal is captured by one of these observatories, it undergoes detailed analysis using advanced computer models and algorithms. This examination can reveal a wealth of information about the signal's origin, where it came from, how far away it is, and even its physical characteristics. Radio signals from space are not just important for scientific discovery, they have practical applications too. For example, signals from satellites enable GPS navigation, weather forecasting, and Earth monitoring. These signals are an essential part of the modern technological world on which we depend daily. Within the constellation Cetus, known as the Sea Monster, lies a star sending whispers across the cosmic ocean. This star is YZ Ceti, a red dwarf much smaller and cooler than our Sun, situated just 12 light years from Earth, relatively close in astronomical terms. Yet what makes YZ Ceti truly fascinating is not the star itself, but the planets orbiting it. At least 3 exoplanets are known to circle this star, and one in particular, YZ Ceti b, stands out. This planet is rocky, Earth-sized, and orbits extremely close to its star, completing a full revolution in just about 1.5 Earth days. Recently, scientists at Bucknell University, led by Professor Jackie Valetson and her colleague J. Sebastian Panetta, made a surprising discovery using the Very Large Array. They detected a repeating radio signal coming from YZ Ceti. The signal, recorded at a frequency between 2 and 4 gigahertz, seems to vary in rhythm with both the star's rotation and the orbit of YZ Ceti b. This pattern suggests an interaction between the magnetic field of the planet, and the star itself. While YZ Ceti b is unlikely to host life due to its extreme proximity to the star and harsh conditions, this discovery is monumental. It demonstrates that we can detect magnetic fields of exoplanets, opening a new window into the study of distant worlds and the search for planets that might be more hospitable for life. Magnetic fields play a crucial role in protecting planets from harmful radiation, and they are vital in maintaining conditions necessary for habitability. This breakthrough could revolutionize how we find life-friendly planets in the future. But what does this mysterious signal truly mean? Why are magnetic fields so essential in our search for life? To answer these questions, we must explore the invisible forces that shape the universe around us. Magnetic fields are among the most important natural forces. They guide the needle of a compass, helping us navigate and assist many animals, such as birds, in their long migrations. They act as a shield, protecting our planet from the harmful solar wind constantly blowing from the sun. Beyond Earth, magnetic fields have a profound influence as well. The sun itself has a powerful and ever-changing magnetic field that controls much of its behavior, from the formation of sunspots to sudden bursts of energy known as solar flares. The sun's magnetic field is the driving force behind these phenomena. Magnetic fields also shape galaxies by guiding the movement of gases between stars and influencing the birth of new stars. Perhaps one of the most fascinating roles of magnetic fields is their potential to help planets support life. A strong magnetic field protects a planet from dangerous radiation emitted by its star. This protection helps preserve the planet's atmosphere, which is essential for maintaining conditions that might support life. This is why discovering a magnetic field on a distant planet like YZ-Ceti-b is so exciting. It could reveal much about the planet's atmosphere and its potential to harbor life. To fully understand how magnetic fields impact the search for life beyond Earth, we need to examine how they influence the signals we receive from space, especially radio waves. Radio signals are a form of energy traveling through space as waves made up of electric and magnetic fields that constantly move and change direction. These fields do not simply travel alone. They interact with other magnetic fields they encounter along the way. When a radio signal passes through a magnetic field, it can experience several changes. For example, its path might bend, a phenomenon known as deflection. The alignment of its electric field, called polarization, can twist. Even its frequency, the number of waves passing a point in a specific amount of time, can shift. These alterations are not random. They carry vital clues about the magnetic field that caused them. By carefully analyzing how a signal changes, scientists can determine the strength and direction of the magnetic field it passed through. This makes radio signals incredibly valuable tools for studying magnetic fields across the universe, offering insights into distant planets and their potential to support life. However, magnetic fields can sometimes cause significant challenges. They interfere with signals, making them weaker and more difficult to detect. This interference distorts the signals, adding layers of complexity that scientists must carefully unravel in order to interpret the data accurately. This is why gaining a deep understanding of magnetic fields is absolutely vital in the field of radio astronomy. By studying how these fields influence radio signals, researchers develop techniques to correct these distortions, allowing them to reveal the hidden information embedded within the signals. To grasp how magnetic fields shape environments that could potentially support life, it helps to look closer to home, specifically at Mars, the red planet in our cosmic neighborhood. Mars is famous for its enormous volcanoes, deep canyons, and signs of ancient water. It has fascinated scientists and dreamers alike for generations. But unlike Earth, Mars presents a unique mystery tied to its magnetic environment, a mystery that challenges our understanding of what makes a planet truly habitable. Mars has a weak and uneven magnetic field which significantly influences its atmosphere and its ability to sustain life. While Earth's magnetic field is generated by the movement of its spinning iron core, Mars's magnetic field is just a faint trace locked within its crust. This leftover magnetism is a remnant from a time long ago when Mars possessed a global magnetic shield. Without a strong magnetic field, Mars lacks the protective barrier that shields its atmosphere from the relentless solar wind, a constant stream of charged particles emitted by the sun. This exposure to the solar wind has had dramatic consequences for Mars. Recent research led by R. Saka from the University of Tokyo suggests that when a planet's core dynamo, the engine driving its magnetic field, shuts down, the remaining weak magnetic field might actually accelerate atmospheric loss, causing the atmosphere to disappear even faster than if there were no magnetic field at all. Simulations reveal that a weak magnetic field can increase atmospheric stripping by up to 6 times compared to having no magnetic field. Here is why this happens. The weak magnetic field lines on Mars are easily pushed around by the solar wind, creating open pathways through which atmospheric particles escape into space, especially on the side facing away from the sun. Over billions of years, this process, known as atmospheric stripping, stripped Mars of most of its atmosphere. In its early history, Mars may have been a warm and wet world, with rivers, lakes, and perhaps even oceans. But as its magnetic field weakened and its atmosphere thinned, the planet transformed into the cold, dry, barren landscape we observe today. This example of Mars vividly illustrates how crucial magnetic fields are to a planet's capacity to support life. Without a strong magnetic shield, even a planet that once had Earth-like qualities can lose the very essentials of life, such as air and water. Beyond our solar system, exoplanets, planets orbiting stars other than the Sun, have become a central focus in astronomy. So far, more than 1,000 exoplanets have been discovered, opening up incredible opportunities to understand the vast variety of planetary systems that exist across our galaxy. One of the most exciting breakthroughs in this field came in late December 2021 when an international team of astronomers using the Hubble Space Telescope detected the first ever magnetic field on an exoplanet. This magnetic field was discovered on a planet named HP 1111b, a Neptune-like planet located approximately 123 light-years away in the constellation Swan. HP 1111b is classified as a hot Neptune, meaning it is similar in size to Neptune but orbits much closer to its star, making its surface extremely hot. Now, turning to the universe at large, we can look back to a time when the cosmos was unimaginably hot and dense. During this early era, light could not travel freely because it was continuously scattered by charged particles. As the universe expanded, it gradually cooled enough for electrons and protons to combine and form neutral hydrogen atoms. This allowed light to escape for the first time, creating a radiation blanket that fills the entire universe. Today, this radiation is no longer the intense heat it once was. It has stretched and cooled into microwave wavelengths because of the universe's ongoing expansion. When scientists observe the cosmic microwave background, CMB, they are effectively looking back in time, capturing a snapshot of the universe's infancy. This ancient light provides crucial insights into the universe's age, composition, and structure. The importance of the CMB in understanding the universe's boundaries lies in its remarkable uniformity and the tiny fluctuations contained within it. These subtle fluctuations represent the earliest seeds of all cosmic structures: galaxies, stars, and clusters. By studying these variations, scientists can infer the density and distribution of matter throughout the universe, helping them develop models that explain how the cosmos has evolved over billions of years. Furthermore, the cosmic microwave background, or CMB, acts like a cosmic boundary, marking the edge of the observable universe. It defines the limit beyond which we simply cannot gather meaningful information. Any region beyond this cosmic horizon lies forever out of reach, because light from those far-off areas has not had enough time to travel to us since the universe began. In this way, the CMB is more than just a leftover echo from a crucial moment in cosmic history. It physically bounds what we can observe and understand about the universe. Wormholes present some of the most intriguing challenges to our ideas about the universe and its boundaries. Traditionally, we imagine the universe expanding outward, with galaxies moving away from each other over unimaginable distances and vast stretches of time. From this perspective, the edges of the universe are not hard limits, but rather regions we cannot see or reach because of the speed limit set by light. Now, imagine a shortcut cutting through this enormous cosmic landscape. A wormhole could act as a bridge connecting two distant points in space and time. Theoretically, this could allow someone to travel across the universe much faster than by following the usual path through empty space between stars and galaxies. This idea raises profound questions. If such shortcuts exist, what does that mean for the concept of distance and the ultimate edge of the universe? Standard scientific theories tell us the universe expands uniformly. But if wormholes are real, they hint at hidden connections between different parts of space that we do not yet fully understand. The edges of the universe, then, may not be as absolute as once thought. They might be pierced or even bypassed. Current knowledge tells us nothing can move faster than light, preserving the fabric of space and time. Yet wormholes challenge this notion, suggesting a far more complex cosmic structure that could permit instantaneous travel. The implications reach far beyond mere travel. They touch on crucial ideas like causality, how cause and effect work, and the very nature of reality itself. While wormholes offer imaginative solutions, they also expose contradictions and anomalies that existing theories struggle to explain. If wormholes exist, scientists may have to rethink and expand the models they use to describe the universe, fundamentally reshaping how we see its structure and limits. The concept of parallel universes opens yet another fascinating dimension of possibility that can deeply affect our understanding of the universe's limits. Picture a vast multiverse, where every decision or event branches off into an infinite number of alternate realities. Each universe exists independently but follows the same basic physical laws that govern our own cosmos. When we consider parallel universes, we begin to question the boundaries we usually accept in existence itself. For example, if multiple realities coexist, What happens to the ideas of time, space, and cause and effect in our universe? In our universe, physical laws impose limits such as the speed of light as a cosmic speed limit and time flowing in a single direction. But in a multiverse scenario, other universes might operate under completely different physical laws or dimensions. This stretches the very foundation of what we think is possible. It forces us to wonder whether our universe is truly unique, or if it is just one version among countless others where fundamental forces behave differently, or where time might even loop back on itself. This challenges the universality of our scientific laws, suggesting they may apply only to our specific reality. Every discovery in our universe could prompt a reassessment of those laws if we take seriously the idea that other realities might have uncovered different truths. The existence of parallel universes implies that the limits we perceive may just be the edges of our current understanding. Expanding our perspective to include these alternate realities allows scientists to explore new theories, question long-held assumptions, and approach the mysteries of cosmology and physics with fresh imagination. Parallel universes do more than challenge our understanding of the cosmos. They invite us to broaden the horizons of what is possible beyond the confines of what we can observe. Extra dimensions also play a crucial role in modern theories about the universe's structure. While we experience the world in three spatial dimensions, length, width, and height, advanced scientific models propose that additional dimensions might exist beyond our immediate perception. These extra dimensions could be hidden or curled up so tightly that they escape detection by current technology. At the core of these ideas, such as string theory, is the notion that fundamental particles are not just tiny points, but rather tiny vibrating strings. The way these strings vibrate depends on the shape and geometry of higher dimensions. Each unique configuration of these extra dimensions affects the physical properties of particles, including their mass and charge, contributing to the complexity and richness of the universe we experience. The importance of extra dimensions goes far beyond theoretical math. They could hold the key to solving some of the universe's deepest mysteries. For example, gravity, which is much weaker than other fundamental forces, might be explained by the existence of these extra dimensions. Scientists suggest that gravity could leak into these additional dimensions, making it appear weaker in the three-dimensional world we live in. This possibility opens a new frontier for understanding the universe's hidden structure, pushing the boundaries of knowledge and challenging what we thought we knew about the fundamental forces that govern everything. Furthermore, the shape of the universe might be profoundly influenced by these extra dimensions, potentially resulting in a far more complex, multidimensional structure than the flat or curved spaces we typically imagine. Visualizing such dimensions challenges our usual perspectives, yet understanding them is crucial for physicists as they wrestle with some of the universe's most puzzling questions. These include the conditions during the universe's earliest moments, the nature of black holes, and the elusive effort to reconcile quantum mechanics with general relativity. Extra dimensions expand the framework through which we comprehend the cosmos, offering a vast, intricate canvas where fundamental forces interact. This broader perspective guides researchers toward a deeper grasp of the very fabric of reality itself. Within this context, brain cosmology offers a unique and fascinating viewpoint on the universe's structure. It suggests that our universe is not an isolated entity, but part of a larger, interconnected framework. Imagine the universe as an immense sheet or membrane, commonly called a brain, floating in a higher dimensional space. This brain represents the familiar three dimensions of space and one dimension of time that we experience. Now, consider the idea that the edge of our universe is not a hard, absolute boundary. Instead, it might be a transitional zone where this brain interacts with additional dimensions or even other brains. In this view, the edge of the universe is not like a wall where everything abruptly stops. Rather, it might be a region where the laws of physics themselves shift and transform due to influences from higher dimensions. These interactions could give rise to remarkable phenomena, such as the creation of entirely new universes or catastrophic events like collisions between brains. When such collisions occur, they could send ripples through our universe, bursts of energy that might explain cosmic events, including the very origin of the Big Bang. By incorporating these higher dimensions into the cosmos's fabric, brain cosmology expands our understanding of cosmic boundaries. Instead of a fixed, finite edge, the universe's boundary becomes a dynamic interface, hinting at a richer, more complex reality that extends beyond what we can directly observe or measure. This invites us to explore a cosmos that is deeply interconnected in ways humanity is only beginning to comprehend. Cosmic topology, a field devoted to understanding the shape and structure of the universe on a grand scale, asks profound questions about the universe's overall form and configuration. Essentially, cosmic topology investigates how the universe is connected and whether it possesses edges or boundaries at all. To visualize this, imagine the universe as a three-dimensional shape, similar to how a two-dimensional surface can curve and connect in various ways. On one end of the spectrum, picture an infinite flat plane that stretches endlessly in every direction. In this scenario, there are no boundaries. One could theoretically travel forever without ever encountering an edge. At the other extreme, envision a finite structure like the surface of a sphere. Here, although the universe is limited in size, one could travel in a straight line and eventually return to the starting point without ever leaving the surface. Different scientific models propose various shapes for the universe, including toroidal forms that resemble reshaped donuts or even far more intricate structures. The fascinating aspect of cosmic topology lies in its challenge to our conventional understanding of space. If the universe is finite but without boundaries, it raises profound questions about what exists beyond our observable realm. Both cosmic topology and the laws governing the universe's expansion influence our comprehension of its composition and ultimate fate. These insights help address whether the universe will continue expanding forever, collapse back upon itself, or reach a stable, eternal state. Ultimately, cosmic topology encourages us to ponder not just where the universe ends, but how it loops back on itself, weaving a complex tapestry of cosmic architecture that remains one of astrophysics' greatest mysteries. Observing the universe's edge presents astronomers with enormous challenges, primarily due to the vastness and complexity of space itself. One of the greatest obstacles is the sheer distance involved. The edge of the observable universe lies so far away that the light we see today began its journey billions of years ago. This means astronomers are essentially peering back into the distant past, making it difficult to fully understand how galaxies and cosmic structures have evolved over time. Another significant hurdle is the limitation of current technology. Observational instruments such as telescopes require precise calibration and often rely on detecting light across various wavelengths. However, not all wavelengths can pass through Earth's atmosphere effectively, limiting our ability to gather data from the farthest reaches of space. To overcome this, astronomers must place instruments in space where there is a clearer, unobstructed view. Yet launching and maintaining these space-based instruments involves complex logistical planning and high financial costs, further complicating efforts to observe the universe's outermost boundaries. Furthermore, the expansion of the universe adds a remarkable layer of complexity to our understanding of the cosmos. The universe is not a static entity. It is in a constant state of growth, stretching its vast boundaries ever outward. This ongoing expansion affects the light traveling from distant celestial objects, causing a phenomenon known as redshift. Essentially, as the universe expands, the wavelength of light stretches, shifting it toward the red end of the spectrum. This effect complicates the detection of faraway objects, making them appear dimmer and more elusive. To interpret these signals accurately, astronomers rely on highly sophisticated instruments and techniques, which continually evolve to meet the challenge of probing deeper into space. Adding to this intricate picture is the fact that our grasp of cosmology, the study of the universe as a whole, is far from complete. Two mysterious components, dark matter and dark energy, dominate the cosmic landscape. Together, they make up a vast majority of the universe's total mass and energy, yet their true nature remains largely unknown. Theories about these enigmatic substances are still being developed, leaving significant gaps in our knowledge. This uncertainty creates further obstacles when trying to understand what lies at the very edges of the observable universe. Each observation is like piecing together a puzzle with missing parts, underscoring both the complexity of space and humanity's relentless quest to unravel its mysteries. Cosmic phenomena, such as black holes, add an extraordinary dimension to this quest. Black holes challenge our understanding of the universe by embodying extreme conditions that test the limits of physics. To imagine a black hole, think of a region in space where gravity is so incredibly powerful that nothing, not even light, can escape its pull. This creates a boundary known as the event horizon, a point of no return. Once anything crosses this boundary, it disappears from the observable universe, taking all information about it with it. This loss of information raises fundamental questions about how the universe operates, challenging our basic assumptions about space, time, and information. Black holes invite us to rethink what we consider the edges of the universe. We often picture space as a vast, infinite expanse with clear boundaries, but black holes reveal that there are regions where normal rules break down. The intense gravitational forces inside and around them warp space and time, bending the very fabric of reality itself. This warping affects how matter and energy behave nearby, prompting scientists to ask difficult questions. What happens to material that falls into a black hole? Does it vanish entirely, or is it transformed in ways we have yet to understand? The theories we rely on, such as Einstein's principles of relativity, become increasingly difficult to apply under these extreme conditions. The study of black holes also intersects with profound questions about the ultimate fate of the universe. As black holes grow by consuming surrounding matter, they influence the formation of galaxies and the evolution of cosmic structures. These massive entities are not mere cosmic oddities. They are active players, shaping the universe's history and future. Their existence challenges scientists to develop new theories that might better describe the strange and complex reality we inhabit. In a similar vein, the discovery of exoplanets, planets orbiting stars beyond our own solar system, has dramatically changed our cosmic perspective. For centuries, astronomers focused almost exclusively on our local celestial neighborhood, assuming that the planets, moons, and other objects within our solar system represented the full extent of what the universe could offer. The identification of exoplanets shattered this limited viewpoint. Imagine standing by a small pond, believing it contains all life, only to realize it is part of a vast, teeming ocean filled with diverse creatures and ecosystems. Each confirmed exoplanet reveals a unique world. Some vast gas giants many times the size of Earth, others rocky planets similar in size and composition to our own. This diversity has inspired a new wave of scientific inquiry focused on understanding the conditions necessary for life to emerge. Could some of these distant worlds harbor environments capable of supporting living organisms? Might intelligent civilizations exist elsewhere in the universe, waiting to be discovered? These questions open new frontiers in astronomy and astrobiology, pushing humanity's curiosity beyond what was once imaginable. In this way, cosmic phenomena, from the expansion of space to black holes and distant exoplanets, continue to deepen the mystery and wonder of the universe. They remind us that while our knowledge has grown tremendously, the cosmos remains vast, dynamic, and full of surprises waiting to be uncovered. Moreover, the techniques employed to detect planets beyond our solar system have revolutionized the way we explore the cosmos. One of the most significant methods involves observing the subtle dimming of a star's light when a planet passes directly in front of it. This transit method has unlocked entirely new paths of investigation. Astronomers now have the remarkable ability to analyze the atmospheres of these distant worlds, searching for telltale chemical signatures. These signatures might hint at the presence of water vapor or even signs of life, sparking hope that we might one day find evidence of organisms beyond Earth. This pursuit has transformed astronomy from a field focused solely on stars and planets into a dynamic, multidisciplinary quest that embraces the very possibilities these celestial bodies represent. The implications stretch far beyond isolated discoveries. They encourage collaboration among diverse scientific disciplines. Astrophysicists, planetary scientists, and biologists have joined forces in interdisciplinary research aimed at understanding not only how these planets form and change over time, but also what they could mean for the future of humanity. The hunt for exoplanets has broadened our perspective dramatically. Instead of seeing our solar system as the center of everything, we now appreciate a vast, diverse, and ever-changing universe filled with countless possibilities. This excitement, fueled by the exploration of new worlds, drives fundamental questions about our place in the cosmos. The universe has ceased to be a mere backdrop for human existence. It has become a vast playground for discovery, holding secrets about life and what lies beyond. Central to this ongoing exploration is the Hubble Space Telescope, an extraordinary instrument positioned high above Earth's atmosphere. Freed from the blurring effects caused by air, Hubble captures breathtaking images and gathers critical data on distant galaxies, stars, and other celestial phenomena. One of its most remarkable strengths is its ability to peer deep into both space and time. By observing light that has traveled for billions of years, Hubble allows scientists to witness galaxies as they existed shortly after the Big Bang, offering invaluable insights into the early universe. This capability enables researchers to estimate the age of the universe and measure the rate at which it continues to expand. Such observations shed light on fundamental questions about the universe's origin and ultimate fate. Beyond galaxies, Hubble has been instrumental in detecting exoplanets, planets orbiting stars beyond our own sun. By studying starlight filtered through these planets' atmospheres, Hubble has helped scientists identify chemical markers that may signal the potential for life beyond Earth. Hubble's observations have also deepened our understanding of black holes, enigmatic objects that warp space and time around them. By tracking how black holes influence nearby stars and gas, Hubble contributes to refining our models of cosmology. Its data, combined with information from other telescopes and observatories, continually pushes the boundaries of our cosmic knowledge. Each new discovery not only answers long-standing questions, but also sparks new ones, extending the limits of what we know. In this way, the Hubble Space Telescope serves as a crucial bridge, linking our current understanding with the vast unknown, illuminating the edges of the universe, while inviting us to explore beyond. Cosmic censorship theory explores one of the most mysterious aspects of black holes and our understanding of the universe. At its heart, the theory suggests that certain cosmic events, especially those involving black holes, should not result in observable contradictions in the fabric of space and time. To put it simply, it proposes that singularities, points in space where gravitational forces become infinite, are always hidden from view by event horizons, which act as boundaries preventing us from seeing these extreme regions. Imagine looking at a calm lake where the surface appears perfectly still and undisturbed. If a stone is thrown into the water, ripples spread across the surface, disrupting the calm. Similarly, singularities inside black holes create profound distortions in space and time. According to cosmic censorship, these distortions are cloaked by event horizons, which prevent any information about the singularity from escaping into the rest of the universe. Because of this, we cannot observe the chaotic, extreme gravitational forces occurring within black holes. This idea has deep consequences for how we understand the boundaries of the universe. It implies that there may be realms completely disconnected from our observable reality. If true, cosmic censorship confirms that while we can study galaxies, stars, and many other celestial objects, there are fundamental limits to what we can know about the most extreme cosmic phenomena. These hidden realms remind us that mysteries remain tightly woven into the very fabric of space and time. Thus, cosmic censorship not only shapes our theories about black holes, but also highlights the ultimate boundaries of human knowledge concerning the universe itself. Even with the incredible advances in space telescopes like Hubble, there are still significant observational challenges. One major limitation is their field of view. Many telescopes are designed to focus intensely on small, specific regions of the sky. This means they might miss larger-scale phenomena occurring beyond their immediate focus. To compensate, astronomers must perform repeated observations over time, stitching together numerous snapshots to build a comprehensive map of the cosmos. Another challenge is sensitivity. Telescopes rely on collecting faint light from distant objects, but this light can be overwhelmed by interference from cosmic dust or background light emitted by nearby stars and galaxies. This background noise can drown out the faint signals from faraway celestial bodies, making it difficult to detect and study them in detail. Despite these challenges, the continuous refinement of technology and collaborative efforts among scientists ensure that each step forward expands our cosmic horizon, revealing more of the universe's wonders while reminding us of the mysteries that remain. Moreover, the wavelengths of light that telescopes can detect fundamentally define their range of observation. Most space telescopes are specifically designed to focus on certain portions of the electromagnetic spectrum, such as visible light or infrared. This specialization, however, means they can miss valuable information present in other wavelengths, like X-rays or radio waves. To gain a comprehensive understanding of the universe, it is essential to combine data collected across these various wavelengths. Another critical factor influencing observation is the telescope's orbit and position. While being above Earth's atmosphere reduces atmospheric interference, telescopes in low Earth orbit remain vulnerable to light pollution from cities, especially if they lack proper shielding. Additionally, telescopes placed in orbits that are not perfectly stable can experience disruptions, which affect their ability to track celestial objects accurately over time. Technological constraints also limit what telescopes can achieve. Issues such as resolution limits and interference from cosmic rays can impair the quality of data collected and complicate its analysis. Cosmic rays are high-energy particles that travel through space and can reach Earth from all directions. These particles originate from powerful events like supernova explosions and active galactic nuclei, which are extremely energetic centers of distant galaxies. As cosmic rays journey through the universe, they interact with magnetic fields and other particles, which can alter their direction and energy. By studying the way cosmic rays arrive at Earth, scientists gain insight into their origins and the environments they pass through. The energy distribution and composition of cosmic rays reveal important details about conditions in space, such as the strength of magnetic fields and the density of intergalactic matter. Cosmic rays can even hint at the locations of energetic phenomena and help map the large-scale structures of the universe, including galaxy clusters. Furthermore, cosmic rays provide an indirect way to study dark matter, a mysterious substance that makes up a significant portion of the universe. By examining patterns in cosmic ray arrivals, researchers can infer how dark matter interacts with particles, offering clues about the universe's composition and the forces shaping its edges. Ongoing research into cosmic rays is therefore vital for expanding our understanding of the cosmos and uncovering mysteries at the farthest reaches of space. At the same time, cosmic background noise poses significant challenges for astronomers. This noise can be thought of as a constant static or whispering that blends into the cosmic symphony. It primarily originates from the cosmic microwave background radiation, which is the leftover glow from the Big Bang and fills all of space uniformly. While this radiation is crucial for understanding the early universe, it can overwhelm weaker signals coming from distant galaxies or dark matter. The difficulty lies in separating the signals scientists want to detect from this pervasive background noise. It is similar to trying to hear a faint conversation in the middle of a cheering crowd. On top of this, telescopes themselves can generate noise through their electronic systems or from interference at ground level, adding layers of complexity to data collection. To overcome these obstacles, researchers use advanced signal processing techniques that filter out noise and extract meaningful information. This requires not only sophisticated algorithms, but also a deep understanding of both the desired signals and the nature of the noise they must filter out. Successfully navigating this cosmic cacophony is crucial for unlocking secrets about the universe's formation and evolution. Gravitational waves are another fascinating phenomenon that offer a new way to explore the universe. These waves are ripples in the fabric of space-time created by some of the most violent and energetic events, such as collisions between black holes or neutron stars. Imagine dropping a stone into a pond and watching the ripples spread outward. Gravitational waves behave in a similar way, traveling through space and carrying vital information about their sources. Unlike light, gravitational waves can pass through matter almost without disturbance. allowing scientists to observe events that would otherwise remain hidden behind stars and galaxies. This unique ability provides a window into phenomena that are difficult or impossible to study with traditional telescopes. By detecting gravitational waves, researchers can determine properties of the objects that produce them, such as their mass, spin, and distance from Earth. Analyzing the patterns of these waves helps astronomers piece together the behavior and history of the universe itself. For example, by studying waves created by merging black holes, scientists learn how these mysterious objects form and evolve, which sometimes challenges long-held theories about their development. Furthermore, gravitational waves open an extraordinary window into the universe's expansion by revealing intricate details about how fast it is growing and the story behind that growth. This emerging field of cosmic investigation unlocks pathways to explore facets of the universe we have yet to fully grasp. For example, gravitational waves can offer insights into the hidden dynamics of neutron stars, those incredibly dense remnants of collapsed stars, or shed light on the mysterious and still elusive nature of dark matter. Acting as cosmic messengers, gravitational waves convey information about the universe's structure in ways that traditional light cannot, enriching our understanding of the cosmos and helping us address some of the most fundamental questions about its essence. Gamma-ray bursts stand among the most powerful explosions witnessed in the universe, often described as cosmic beacons that guide scientists on their journey through deep space exploration. These bursts unleash staggering amounts of energy across a vast range of wavelengths, with gamma rays leading the charge. Picture these bursts as intense flashes of light triggered when massive stars undergo violent collapses known as supernovae, or when two dense neutron stars collide, generating energy surges so bright they outshine entire galaxies, even if only for fleeting moments. The extraordinary brightness of gamma-ray bursts is what makes them so significant. They are visible from incomprehensible distances, sometimes billions of light years away. This unique property allows astronomers to peer deeper into the universe's past than many other celestial phenomena. Since gamma-ray bursts often occur in regions far removed from our own galaxy, they serve as cosmic lighthouses, illuminating the distant reaches of space and offering clues about the conditions that prevailed in the early universe. Beyond their spectacular displays, studying these bursts has profound implications for understanding cosmic structures and the processes shaping them. By carefully analyzing the light emitted during these events, scientists can deduce the composition and behavior of the interstellar medium where the bursts take place. This knowledge unveils critical details about star formation, the life cycles of stars, and the evolution of galaxies on a grand scale. Gamma-ray bursts also challenge our grasp of fundamental physics, pushing the boundaries of what we know about gravity, matter, and energy. Their study inspires the development of new technologies and instruments designed to detect and decode signals from these remote cosmic explosions. As these tools grow ever more sophisticated, the horizons of our cosmic exploration expand, revealing hidden mysteries and deepening our understanding of the universe's vast and complex phenomena. The brilliant dance of light from gamma-ray bursts is far more than a stunning spectacle. It actively drives our quest to unravel the universe's secrets. The Oort cloud can be imagined as an immense spherical shell enveloping our solar system, marking the frontier of our current knowledge about where our cosmic neighborhood ends. Visualize a vast swarm of icy bodies lurking far beyond the orbits of the outermost planets, forming an invisible fence that defines the solar system's edge. This distant region is believed to harbor countless comets and frozen remnants left over from the solar system's formation, providing a frame for how we consider what lies beyond our immediate cosmic vicinity. Although we have never directly observed the Oort cloud, scientists infer its presence from the behavior of long-period comets, which seem to emerge from this remote zone. Occasionally, these comets journey inward toward the sun, offering rare glimpses of the material inhabiting this far-off region. The Oort cloud represents more than just a boundary. It challenges our perception of the universe's edge by suggesting that the solar system is not an isolated island, but part of a much larger and far more intricate cosmic environment. This remote region provokes compelling questions about what else might exist beyond what we can currently see. It stands as the outer frontier of the solar system's influence, hinting at the possibility of mysterious phenomena, undiscovered star systems, and hidden celestial bodies waiting to be found. Instead of viewing the universe as a finite space, the Oort cloud invites us to embrace a perspective filled with endless possibilities, inspiring both scientists and dreamers to ponder the vast unknown expanses that lie just beyond our reach. Quantum mechanics holds a central role in shaping our understanding of the universe, especially when examining its most extreme and enigmatic aspects. To appreciate this, consider that at the tiniest scales of reality, particles behave not merely as solid objects, but also exhibit wave-like properties, blurring the clear-cut rules of classical physics. This fundamental principle gives rise to phenomena that seem strange and counterintuitive, fundamentally transforming how we comprehend everything from the fabric of space-time to the very essence of energy itself. In extreme environments, such as black holes and the Big Bang, quantum mechanics introduces revolutionary ideas like uncertainty and superposition, which challenge the classical view of a deterministic universe. For example, inside a black hole, gravity compresses matter to unimaginable densities, creating conditions where quantum effects become impossible to ignore. Theories suggest that near the event horizon, the point beyond which nothing can escape, quantum fluctuations allow particles to appear and vanish spontaneously. These mysterious processes could lead to the creation of new universes or relate to the famous information paradox, the puzzle surrounding what happens to information consumed by black holes. Similarly, when studying the universe's earliest moments during the Big Bang, quantum mechanics provides critical insights into how particles interacted at incredibly high energies and densities. Tiny quantum fluctuations during this time may have planted the seeds for cosmic structures, giving rise to galaxies, clusters, and the large-scale universe we observe today. These subtle variations in energy density, ripples in the fabric of the early universe, could be the very foundation from which all cosmic phenomena emerged. The dance between quantum mechanics and the vast phenomena of the cosmos reveals a strange and essential world that pushes the limits of our understanding. It challenges the way we see reality and offers new directions for theories about the farthest reaches of space and the deepest moments in time. To truly grasp the universe's nature, one must accept the strangeness of the quantum world, a place where familiar rules no longer hold, exposing a reality far more intricate and connected than we ever imagined. String theory steps into this mystery with an idea that transforms our view of the universe. Traditionally, we have thought of the universe as built from tiny point-like particles, the fundamental building blocks of everything around us. But string theory proposes something much more curious. These particles are not mere points, but tiny strings vibrating in different ways. Picture these strings as minuscule rubber bands, each oscillating with its own unique frequency. The way each string vibrates determines the properties of the particles we see, like their mass or their electric charge. This idea alone reshapes everything, especially when we turn our attention to the edges of the universe. Instead of seeing the universe as a simple three-dimensional space with a clear edge, string theory suggests there could be many more dimensions, possibly up to 10, that we cannot perceive with our senses. These hidden dimensions might influence what happens at the boundaries of our universe. Rather than abrupt end, the edge might be a kind of doorway or portal to these unseen realms. This idea challenges our traditional concept of an edge as a final barrier and suggests that what lies beyond could be intertwined with these extra dimensions, subtly altering how we experience reality itself. String theory encourages us to think of the universe as a vast, interconnected whole. Instead of being an isolated island in space, the cosmos could be part of a much larger, more complex, multidimensional structure. This insight changes how we imagine the edge of the universe. It may not be a limit, but a merging point where the familiar and the unknown meet, opening up endless possibilities that stretch far beyond what we can currently understand. In contrast to older views that treat the universe's edge as a hard stop, string theory paints a picture of fluid boundaries where space itself blends into a vibrant fabric of dimensions yet to be explored. Another captivating idea is the holographic principle. It proposes that all the information inside a volume of space can be captured on a two-dimensional surface, similar to how a hologram projects a three-dimensional image from a flat plane. Imagine the universe's full complexity, with its countless dimensions and phenomena, encoded on a simple two-dimensional boundary, like the surface of a black hole. This concept shakes the foundation of how we perceive space and dimensions. It implies that the physical laws we observe in three dimensions may arise from processes happening on this two-dimensional boundary. If we think of the universe as having edges or limits, the holographic principle offers a way to understand how all the vast information within space could fit onto a seemingly smaller surface. The detailed nature of our three-dimensional reality might not be directly contained within space itself, but instead emerge from a more basic underlying layer that extends beyond our perception. This idea could also explain mysteries about the universe's edges, such as the cosmic horizon, the point beyond which we cannot see. It suggests that our universe may be bounded at some level, encoded like data on a surface, influencing how gravity, black holes, and space-time itself behave. By exploring these edges, the holographic principle gives us a glimpse into the universe's potential limits and invites us to rethink what reality truly means at its core. Finally, the simulation hypothesis takes us to an even more provocative place. It suggests that our entire reality might be a highly sophisticated simulation created by an advanced civilization. This idea leads us to question the nature of consciousness, existence, and the universe itself. When viewed alongside theories about the universe's edge, this hypothesis widens the horizon even further. Imagine the edge of the universe as the shoreline of a vast ocean of knowledge. Beyond that shore lies the unknown. The simulation hypothesis asks us to consider that our entire perceived universe could be just one part of a grander reality, designed and controlled by beings capable of manipulating those boundaries. If our universe is a simulation, then these edges are not the ultimate limits, but programmed constraints within an artificial environment. In this view, the laws of physics resemble the rules of a game, defining how players move and interact in a controlled space, yet potentially adjustable by the creators. This opens up thrilling questions about what exists beyond our known boundaries, and whether the limits we observe are fixed or flexible, depending on the intentions of those who crafted this cosmic simulation. Together, these ideas challenge us to reconsider what we think we know about the universe. They invite us to embrace the strange, the hidden, and the mysterious, revealing a cosmos far richer and more complex than ever before imagined. Additionally, some interpretations of the simulation hypothesis propose that just as computer simulations vary dramatically in complexity and rules, the universe itself might consist of multiple layers. Each layer could represent a distinct simulation or reality, intertwined with one another in ways we have yet to fully understand. These layers could range from simple to infinitely complex, suggesting that our own reality is only one of many interwoven dimensions. Universal edge theories emerge as tools that help us speculate about what lies beyond the simulation we experience firsthand. These ideas open doors to concepts like parallel worlds, alternate dimensions, or even entirely different forms of existence that are currently beyond human comprehension. Combining the simulation hypothesis with universal edge theories forces us to reconsider the very nature of reality, our position within it, and the possibility of other realms beyond what we perceive in daily life. It challenges us to question whether our universe is nothing more than data flowing through a vast program, created for exploration, understanding, or perhaps other purposes that remain undiscovered. This perspective encourages a profound shift in thinking, moving us away from viewing reality as fixed and absolute to seeing it as fluid and layered, shaped by forces and structures that may be fundamentally different from anything we have encountered. The anthropic principle offers a captivating insight into why the universe appears fine-tuned for life. At its heart, this principle suggests that the universe's fundamental properties are precisely calibrated to allow conscious beings to emerge, beings capable of observing, reflecting, and asking questions about their own existence. Imagine the universe as a cosmic stage where conditions must be perfectly balanced for life to take root and thrive. If the fundamental forces of nature or the values of essential constants were even slightly different, life as we know it might never have emerged at all. This idea shifts our understanding from viewing the universe solely through natural laws to considering the crucial role of observers within it. There are two main interpretations of the anthropic principle: the weak and the strong. The weak version simply states that the universe must permit life to exist because we are here to observe it. In contrast, the strong version proposes that the universe exists specifically because it must support conscious observers. Exploring these ideas deepens our understanding of cosmology and the concept of fine-tuning. Some scientists suggest that countless universes may exist in a vast multiverse, each governed by different laws and constants. Within this framework, it is not surprising that we find ourselves in a universe capable of supporting life, simply because it is one among many realms where life is possible. This principle pushes us to explore the very nature of existence itself, blurring the boundaries between science, philosophy, and our place in the grand tapestry of reality. It expands our perspective, inviting us to imagine the universe not as a cold, indifferent expanse, but as a domain where consciousness plays a central and active role. Speculative technologies like warp drives fuel fascinating discussions about the limits of the universe and what might lie beyond. A warp drive, as conceived in theoretical physics, proposes a method of faster-than-light travel by manipulating space itself. Picture a bubble of distorted space surrounding a spacecraft, contracting space in front of it and expanding space behind it, allowing the craft to traverse vast cosmic distances without breaking the conventional speed limit set by physics. This concept challenges long-held assumptions about how fast travel can be and what boundaries the universe imposes. The implications of such technology reach far beyond shorter travel times. If a warp drive could become a reality, it might revolutionize our understanding of the universe's structure and its true limits. Scientists currently believe that the universe is finite and continuously expanding, with galaxies moving away from each other. However, the existence of warp drives could imply that parts of the universe, once thought inaccessible, could become reachable, forcing us to rethink what it means for the universe to have edges or boundaries. Together, these ideas invite us to explore reality from new and exciting angles, questioning everything we once took for granted about existence, space, and the nature of life itself. Moreover, warp drives represent a tantalizing gateway to realms that lie beyond the grasp of known physics. These theoretical machines could enable humanity to traverse vast regions of space once considered unreachable by conventional means of travel. Such a breakthrough would compel us to rethink cosmic geography itself, challenging established maps of the universe. This reevaluation could revolutionize our study of celestial phenomena, granting access to areas of the cosmos previously shrouded in mystery and beyond our observational reach. Yet, warp drive technology remains firmly in the realm of speculation, bringing with it profound questions about the nature of causality, the fabric of space-time, and the very essence of reality. Should such travel become feasible, it would not merely reshape how we navigate the universe, but could fundamentally upend the principles underpinning physics, pushing scientists to delve deeper into the underlying structure of existence. Alongside warp drives, the concept of tachyon particles pushes the boundaries of what we understand about speed and motion. Tachyons are hypothetical particles theorized to always travel faster than light. To grasp their significance, it is important to understand how they differ from ordinary particles. Regular particles, like those forming all matter we encounter daily, gain mass as they accelerate toward the speed of light, making it impossible to surpass that ultimate speed barrier. In contrast, tachyons would lose mass as they speed up, allowing them to break through this cosmic speed limit. If tachyons exist, they might offer us a glimpse into dimensions beyond our universe, often called the multiverse. By traversing these realms faster than light, tachyons could carry signals or data almost instantaneously across vast cosmic distances, bridging gaps that normal particles cannot cross. This property invites us to reconsider the very structure of space-time. Detecting tachyons or their effects might unlock clues about alternate realities or provide insights into the universe's earliest moments, before light could roam freely through space. Though still speculative, the study of tachyons opens exciting theoretical pathways that could broaden our understanding of the cosmos, potentially reshaping our view of reality's fabric and what lies beyond the known universe. Time dilation and relativity also play pivotal roles in our cosmic understanding, especially as we explore ideas about the universe's vastness and its possible boundaries. Einstein's theory of relativity reveals that time is not fixed. It changes depending on how fast an object moves and its position within gravitational fields. Imagine a spacecraft speeding through space at a significant fraction of light speed. For the astronauts inside, time would pass normally, but for observers back on Earth, years could elapse in what feels like moments for those aboard the ship. This phenomenon, known as time dilation, illustrates that the faster you travel, the slower time passes for you relative to someone who remains still. It sparks profound questions about what might lie beyond the limits of our perception. Given the immense distances between galaxies, the light we see from distant stars and galaxies has traveled for billions of years. Should humanity one day achieve near light speed travel, explorers could experience comparatively brief journeys while witnessing cosmic history unfolding over millennia back on Earth. Relativity also suggests that the universe's edge might be far less fixed than previously thought. The universe is continuously expanding, and since time behaves differently under varying circumstances, it opens up discussions about the existence of multiple universes and dimensions beyond our current grasp. Time dilation thus becomes not only a scientific curiosity, but a doorway to speculative theories about the universe's true extent and the possibility of realms far beyond our known experience. It invites us to explore not only space, but the very nature of existence itself. As we stand on the verge of a new era of cosmic exploration, emerging technologies promise to radically enhance our understanding of the universe's limits. Advanced telescopes equipped with cutting-edge sensors will be able to capture light from the farthest reaches of space, probing parts of the cosmos currently hidden from view. These instruments will detect light across a range of wavelengths, unveiling secrets invisible to our current technology. Alongside this, the rise of powerful computers and artificial intelligence will transform how we analyze the enormous volumes of data gathered from the cosmos. AI systems could identify subtle patterns and anomalies in cosmic background radiation or other phenomena, offering vital clues about the universe's structure, its expansion, and even its ultimate fate. This capability will revolutionize cosmology, helping refine our models of how galaxies form, collide, and evolve over billions of years. Progress in space travel technologies could also enable human-made probes to venture into previously unreachable corners of the universe. Such missions would offer direct measurements and first-hand experience of cosmic environments never before encountered, deepening our understanding of phenomena such as dark matter, the intergalactic medium, and cosmic radiation's role in shaping the cosmos. Imagine a probe crossing the vast expanse between galaxies, collecting invaluable data that could reshape astrophysics. Furthermore, advancements in instruments like gravitational wave detectors will reveal unseen aspects of the universe, ripples in space-time caused by colossal cosmic events such as black hole mergers or neutron star collisions. As these detectors become more sensitive, they will unlock secrets about the universe's dynamic processes, expanding our comprehension of its boundaries and underlying forces. Together, these emerging technologies promise not just to expand our knowledge, but to challenge the very frameworks we use to understand the cosmos. As new dimensions of information unfold, our picture of the universe will shift, inspiring renewed curiosity and insight. Among the universe's greatest mysteries lies the nature of its expansion. Much like a balloon stretching as it inflates, the universe is expanding, pushing galaxies away from one another. This continuous expansion reshapes the cosmic landscape, driving questions about what lies at the horizon of the observable universe, what drives this growth, and how it might influence the ultimate fate of everything we know. However, observations reveal that the universe's expansion is not just continuing, it is speeding up. What exactly fuels this mysterious force, often called dark energy, remains one of the greatest puzzles in modern science. Despite making up a large portion of the universe's total content, dark energy's true nature is still largely unknown. This invisible force seems to push galaxies apart at an ever-increasing rate, defying our previous understanding of cosmic dynamics. Another profound enigma concerns the very limits of what we can observe. The observable universe is like a vast bubble, defined by the speed of light and the age of the cosmos. Because light travels at a finite speed, we can only see objects whose light has had enough time to reach us since the beginning of the universe. This creates a cosmic horizon, a boundary beyond which lies an uncharted expanse. Beyond this horizon, space may stretch endlessly, or it might harbor phenomena that challenge everything we think we know about physics. Then there is dark matter, an invisible form of matter that neither emits nor absorbs light or any other kind of energy. Its existence is inferred only through its gravitational influence on the matter we can see: stars, gas, and galaxies. Dark matter plays a crucial role in shaping the universe's large-scale structure, acting as a kind of cosmic scaffold around which galaxies and clusters form and evolve. Yet, despite decades of research, its composition remains elusive, hiding a deeper layer of reality that still escapes human understanding. Adding to the mystery is the idea that our universe might be just one among many. The multiverse theory suggests the existence of countless other universes, each potentially governed by different physical laws and constants. If true, this concept would drastically reshape our place in the cosmos, turning our universe into a single thread in an unimaginably vast cosmic tapestry. These profound mysteries underline the limits of human knowledge, pushing scientists closer and closer to the edges of understanding. Every new discovery not only reveals hidden truths, but also reshapes our perception of what the universe really is. It reminds us that, for all our progress, so much remains to be uncovered. Unexplained phenomena have always served as catalysts for scientific progress, driving the expansion of knowledge beyond existing frameworks. Imagine standing at the edge of a vast ocean where the horizon stretches endlessly. Just as sailors of old were inspired to explore beyond the visible edge, scientists today are compelled to investigate the mysteries lingering in the cosmos. Dark matter and dark energy, along with phenomena like gravitational waves, challenge established ideas and force researchers to rethink fundamental assumptions. For example, the gravitational effects of dark matter reveal that the visible universe is only a fraction of what truly exists. This realization has led scientists to broaden their theories, incorporating unknown and elusive components that influence the formation of galaxies and cosmic structures. Similarly, the accelerated expansion driven by dark energy upends the old view that gravity always slows cosmic growth. Instead, it suggests that some invisible force is pushing space itself to expand faster and faster. This challenges not just our understanding of gravity, but also the very fabric of the universe. Gravitational waves, ripples in space-time caused by massive cosmic collisions, have opened a new window onto the universe. These faint signals provide direct evidence of dynamic events like merging black holes and neutron stars, revealing a universe alive with dramatic interactions that reshape theoretical models. Each of these enigmatic phenomena pushes the boundaries of science, driving researchers to propose new theories or refine existing ones. This ongoing quest reflects humanity's insatiable curiosity, where every mystery solved unfolds further questions, stretching our understanding across space and time. Astronomical anomalies, unexpected or unexplained cosmic phenomena, are crucial puzzle pieces that can overturn established scientific theories. When astronomers observe stars behaving strangely or galaxies with unusual mass distributions, these anomalies expose the limits of current models. They force scientists to probe deeper and reconsider accepted ideas. Take dark matter as an example. It was initially proposed to explain why galaxies spin at speeds that should tear them apart. The idea of an invisible, gravity-exerting substance filled the gaps in knowledge. Yet, despite this hypothesis, the true nature of dark matter remains a profound mystery, hinting that the universe may operate under principles still beyond our grasp. Similarly, the discovery that the universe's expansion is accelerating introduced dark energy as a new cosmic player. This revelation contradicts previous expectations that gravity would slow expansion over time. Instead, some unseen force appears to be driving space apart faster than ever, demanding new explanations and theories. Anomalies like these are not mere curiosities. They spark innovation. They compel scientists to explore new ideas, whether through quantum physics, modified gravitational laws, or concepts of extra dimensions. In doing so, they expand the horizons of cosmic knowledge and push science into uncharted territory. At the very boundaries of understanding, scientists face the challenge of reconciling theory with observation. When data contradicts established models, researchers engage in a rigorous process of verification, using advanced technology and simulations to ensure accuracy. Only when the data withstands scrutiny do they reconsider the theoretical frameworks. This iterative process, questioning, testing, refining, illustrates the dynamic and self-correcting nature of science. Sometimes it leads to minor adjustments, other times to revolutionary shifts in perspective. For example, the recognition of accelerating cosmic expansion necessitated the introduction of dark energy, fundamentally altering cosmology. Collaboration among scientists worldwide fuels this progress, blending insights from different fields to address contradictions and develop new models. These collective efforts deepen our cosmic understanding and inspire new avenues of exploration. Deep space phenomena serve as portals to understanding the universe's complexities. Observations of distant galaxies reveal a sprawling cosmic tapestry woven with events dating back to the universe's earliest moments. By studying the faint light from these ancient galaxies, astronomers gain insight into their formation and evolution, tracing the intricate processes that shaped them over billions of years. One of the most significant revelations from deep space is the evidence for dark matter. Though invisible, its gravitational effects hint at its presence, reshaping our concepts of gravity and how cosmic structures assemble. Likewise, the discovery of cosmic microwave background radiation, a faint afterglow from the universe's infancy, offers a snapshot of conditions shortly after the Big Bang. This radiation supports the theory that the universe began as a hot, dense state before expanding and cooling into the cosmos we know today. Together, these discoveries form a mosaic of understanding, continuously evolving as new data arrives and new questions emerge. The universe remains a vast and mysterious frontier, inviting humanity to explore ever further into its depths. The explosive deaths of massive stars known as supernovae are among the most dramatic and significant events in the cosmos. These spectacular phenomena do more than just mark the end of a star's life. They are fundamental to spreading elements throughout the universe. When a supernova erupts, it forges heavy elements like iron, gold, and uranium in its fiery heart, then scatters these building blocks across space. This cosmic dispersal seeds future generations of stars, planets, and ultimately life itself. But the importance of supernovae goes beyond element creation. They serve as vital tools for astronomers by acting as standard candles, luminous beacons whose intrinsic brightness is known. By comparing their true brightness with how bright they appear from Earth, scientists can accurately measure cosmic distances. This method has been essential for mapping the expansion of the universe, revealing not only that space itself is stretching, but also uncovering the mysterious force, dubbed dark energy, that appears to be accelerating this expansion. In recent years, another revolutionary development has expanded our window into the cosmos, the detection of gravitational waves. These ripples in the fabric of space-time arise when massive objects like black holes or neutron stars collide, creating waves that travel across the universe at the speed of light. Their discovery has confirmed Einstein's century-old predictions in his theory of general relativity, while offering an entirely new way to observe cosmic phenomena that were once invisible. Gravitational wave astronomy allows scientists to study events hidden from traditional telescopes, unveiling secrets about the universe's most violent and enigmatic processes. Together, the study of supernovae, gravitational waves, and other cosmic phenomena continues to unravel the mysteries that surround us. From probing the elusive nature of dark matter and dark energy, to understanding how galaxies and large-scale structures formed, every observation adds a new piece to the cosmic puzzle. Each new discovery fuels humanity's relentless quest to understand where we come from and what the universe truly is. Among the most fascinating cosmic objects are quasars, short for quasi-stellar objects, which rank as some of the brightest and most energetic beacons in the universe. At their heart lies a supermassive black hole, millions to billions of times more massive than the Sun, residing in the center of a distant galaxy. As gas and dust spiral toward these black holes, they are compressed and heated to unimaginably high temperatures, emitting tremendous energy that can outshine entire galaxies. Quasars are not only dazzling light sources, they are time machines illuminating the early universe. Because many quasars shine with light emitted billions of years ago, they offer astronomers a unique glimpse into the conditions and processes occurring shortly after the Big Bang. By analyzing the light from these distant quasars, scientists can study the composition of the early universe, how matter was spread across space, and how the first galaxies and stars began to take shape. Moreover, quasars push the boundaries of physics itself. The extreme gravitational and energetic conditions surrounding these objects create environments where the laws of physics are tested to their limits. Observations of quasars give insight into how matter behaves under intense gravitational forces and provide challenges to our understanding of general relativity and quantum physics. Quasars also play a crucial role in exploring the universe's expansion. By measuring the light they emit over vast distances, astronomers can calculate the speed at which the universe is growing and how this rate has changed over cosmic time. These measurements help shed light on the nature of dark energy, the mysterious force that drives the accelerating expansion of space. In exploring the farthest reaches of the cosmos, scientists have even begun to confront the idea of nothingness at the edges of the universe, a concept that challenges our most fundamental ideas about existence. Here, nothingness refers not simply to empty space, but to regions devoid of matter, light, and even the familiar forces that shape reality as we know it. Such a notion pushes the boundaries of physics and philosophy alike. If areas of true nothingness exist, it could mean that our universe is just one of many in a vast multiverse, a collection of different universes, each with its own laws and properties. This raises profound questions about whether these other universes could ever be reached or understood, or if they lie forever beyond our grasp, separated by an incomprehensible void. Moreover, the existence of nothingness might force a rethink of how the universe itself evolves. It could suggest that the cosmos we observe is only one phase in a grander cycle of expansion and contraction, a chapter in an ongoing cosmic story rather than a simple beginning followed by endless expansion. Such possibilities challenge the prevailing cosmological models and open new paths for inquiry into the true nature of reality. From the explosive deaths of stars to the dazzling brilliance of quasars, from ripples in spacetime to the profound mysteries of nothingness, each discovery deepens our understanding of the universe and our place within it. The cosmos remains a vast, largely unexplored frontier, inviting humanity to keep searching, questioning, and imagining the unimaginable. Moreover, when we consider the idea of nothingness, it forces us to challenge the very essence of reality itself. The fundamental concepts of space and time, which have long been the cornerstones of how we understand and navigate the universe, may lose their meaning at these extreme edges. This suggests that our perception of the universe's boundaries is far more fluid and elusive than previously believed. Such a discovery pushes us toward deep existential questions about what space truly is. If parts of the cosmos exist in a state of absolute nothingness, what implications does this have for life and consciousness? Does the significance of existence come from its contrast against the vast emptiness that surrounds it? These revelations provoke profound philosophical debates, intertwining the realms of science and philosophy, compelling us to reflect on our place in the cosmos. The discovery of nothingness at the universe's borders could rewrite everything we thought we knew about reality, opening new doors to unexplored realms of inquiry and understanding. Turning to the faint galaxy clusters scattered throughout space, these groups of galaxies, bound together by gravity, act as invaluable cosmic landmarks. Though they are often located far beyond our own galaxy and appear faint, this subtlety is not a hindrance, but a unique advantage. It allows scientists to peer deeper into the mysteries of dark matter, dark energy, and the evolution of the universe's structure. Observing these distant clusters is like performing cosmic archaeology. The light we capture today actually departed from those clusters billions of years ago offering a rare glimpse into the universe's ancient past. By studying their composition and distribution, astronomers can collect vital information about how matter is spread throughout the cosmos. This data is crucial in understanding dark matter, an invisible substance that, despite its elusive nature, constitutes a significant portion of the universe's mass. Furthermore, the way light bends as it passes near these clusters, known as gravitational lensing, offers essential clues about their mass and gravitational pull. Picture using a magnifying glass to focus light onto a faraway object. Gravitational lensing operates on a similar principle, enabling us to see objects otherwise too distant or faint to detect. This warping of light not only reveals the cluster's structure, but also provides a window into the distribution of dark matter across the universe. Faint galaxy clusters also hold the key to understanding the expansion of the universe itself. The properties of these clusters help scientists investigate the influence of dark energy, a mysterious force believed to be driving the accelerating growth of the cosmos. By analyzing how these clusters interact and how far apart they are, researchers can piece together a history of cosmic evolution shaped by dark energy over billions of years. Though faint galaxy clusters may seem insignificant at first glance, they are in fact interwoven into the very fabric of cosmic exploration. They guide us in uncovering the strange and elusive forces governing the universe, bridging gaps in our understanding from the earliest moments of existence to the present accelerating expansion, and deepening our pursuit of cosmic knowledge. Fast radio bursts, often called FRBs, are among the most fascinating and enigmatic phenomena in astrophysics today. These brief yet intense flashes of radio waves emerge from staggering distances, potentially billions of light years away. Lasting only a few milliseconds, these bursts unleash more energy than the sun emits in nearly 100 years. What makes these cosmic signals especially compelling is their mysterious origin. Each burst appears to come from deep space, but so far we have detected only a small fraction of them. Their source remains largely unknown, inspiring a wide range of hypotheses. Scientists have suggested possibilities ranging from the collapse of massive stars to interactions involving neutron stars, or even the extreme magnetic effects of magnetars, which are neutron stars with extraordinarily strong magnetic fields. The frequency and manner in which FRBs are scattered across the sky provide researchers with vital clues about the cosmic environment through which their signals travel. For example, the dispersion of these radio waves as they journey through space reveals the presence of matter that cannot be seen directly. This information helps scientists build a map of cosmic structures, shedding light on how light and signals move across the vast expanses of the universe. In this way, fast radio bursts serve not only as mysterious cosmic events, but also as tools that deepen our understanding of the invisible scaffolding holding the universe together. Moreover, the remarkable ability to detect these bursts and accurately pinpoint their locations opens exciting new pathways for exploring the evolution of the universe. By carefully analyzing the patterns and frequencies of these cosmic events, researchers hope to unlock hidden secrets about the conditions that prevailed in the early universe. This, in turn, sheds light on how galaxies formed and the complex ways in which cosmic matter interacts across vast distances. The mysterious nature of fast bursts of signals, FBS, invites scientists to delve deeper into the vibrant and dynamic dance of celestial bodies. It inspires fresh discoveries and continually enriches our understanding of the cosmos. Among the vast expanses of space, cosmic voids stand out as immense regions that contain very few galaxies compared to the denser areas surrounding them. These enormous stretches of near emptiness, often spanning hundreds of millions of light years, can be thought of as the silent, hollowed-out spaces within the universe. Studying these voids allows astronomers to grasp not only the large-scale architecture of the universe, but also to glimpse the edges of our cosmic neighborhood. The very existence of cosmic voids points to a fundamental aspect of the universe's composition. As galaxies gather and clump together under the relentless pull of gravity, they weave a vast web-like structure across space. This cosmic web features dense filaments and clusters of galaxies that surround the emptier voids, creating a complex and beautiful tapestry. Rather than being uniformly spread out, matter is concentrated in specific regions, with enormous stretches of emptiness in between. When discussing the boundaries of the universe, we often refer to the limits of what we can observe, the observable universe. Cosmic voids play a key role in this conversation because their presence offers clues about how matter and energy are distributed on the largest scales. While we can see out to a certain distance with telescopes, the universe likely extends far beyond what we can detect. These vast, sparsely populated voids might continue into regions beyond the edges of our observable universe. The existence of these voids also raises fascinating questions about the universe's shape and structure, its topology. If we imagine the universe as a three-dimensional balloon expanding over time, then cosmic voids might represent patches on the balloon's surface that have stretched less than others. This challenges our understanding of what lies beyond the visible universe and prompts profound questions about the ultimate fate of the cosmos. Does the universe extend infinitely, or is it contained in some mysterious, uncharted way? Cosmic voids are far more than just empty space. They embody the complexity and diversity of the universe, illustrating how the idea of boundaries might be interpreted on a cosmic scale. While the observable universe has clear limits, the true nature of the cosmos could reveal landscapes vastly different from anything we have yet explored. Cosmologists play an essential role in unraveling these mysteries about the universe's edge, the farthest regions we can observe, and the limits of human understanding. Combining observational science with theoretical frameworks, they use advanced telescopes and sophisticated instruments to capture faint light from distant galaxies. These observations enable the creation of detailed maps of the universe, revealing its composition and structure, including immense cosmic features like galaxy clusters and the elusive distribution of dark matter. Beyond observation, cosmologists rely on the principles of general relativity and fundamental physics to develop models explaining how the universe has evolved since its inception. By studying phenomena such as the cosmic microwave background radiation, the faint afterglow from the birth of the universe, they gain insights into early conditions and how the universe has expanded over billions of years. By tracking how galaxies move and cluster, cosmologists can infer the overall shape and curvature of the universe. The pursuit of understanding the universe's edge also involves exploring cosmic inflation, a rapid expansion believed to have occurred just after the Big Bang. This theory suggests the universe grew exponentially in a very short time, laying the groundwork for the cosmic structures we observe today. Researchers work tirelessly to confirm or challenge this theory through careful analysis of the cosmic microwave background and the study of galaxies that existed when the universe was much younger. Another critical focus is dark energy, a mysterious force thought to drive the accelerated expansion of the universe. By measuring the distribution of galaxies and observing light from distant supernovae, cosmologists attempt to understand how this expansion influences cosmic structures and what it might mean for the universe's ultimate fate. Their ongoing research continually broadens our understanding of the universe's edges while sparking new questions about what lies beyond the limits of our current observations. Together, these contributions allow cosmologists to weave a comprehensive story about the universe, bridging gaps in knowledge and illuminating mysteries that remain just out of reach. In this grand quest, astrophysics and cosmology emerge as two closely linked branches of astronomy, each vital to understanding the universe's vastness. Astrophysics zooms in on the physical properties and behaviors of individual celestial bodies, from the life cycles of stars to the enigmatic nature of black holes. Cosmology, in contrast, steps back to consider the universe as a whole, its origins, evolution, structure, and ultimate destiny. These fields intersect vividly when investigating the universe's boundaries. Astrophysics provides essential tools and insights for analyzing phenomena that shape our cosmic environment. For example, understanding how stars live and die is crucial for cosmology because these processes forge and distribute the elements that form galaxies, planets, and ultimately the building blocks of life itself. Together, these scientific disciplines paint a richer, more detailed picture of the cosmos and our place within it. Conversely, Cosmological theories provide a vast and profound framework within which astrophysics can delve into greater detail. The Big Bang theory, often regarded as a cornerstone of modern cosmology, proposes that the universe has been expanding ever since its inception. Astrophysicists take this fundamental concept and apply it in practical ways, such as investigating the redshift of distant galaxies. This redshift refers to how the light emitted from these galaxies stretches toward longer wavelengths as they move away from us, offering clear and compelling evidence that the universe is indeed expanding. This discovery helps scientists draw the line between what is observable and what remains beyond our current reach, raising profound questions about how much of the cosmos lies outside our ability to see or measure. Together, cosmology and astrophysics work hand in hand to address some of the most fundamental mysteries, including the elusive nature of dark matter and dark energy. These enigmatic components play a significant role in shaping the universe's expansion and its large-scale structure. Astrophysical observations of phenomena like gravitational waves and the cosmic microwave background radiation continuously feed into cosmological models, refining our understanding of the universe's composition and its evolutionary path. While astrophysics allows us to understand the intricate details of stars, galaxies, and cosmic events, cosmology offers the grand narrative, the overarching story that enables humanity to push the boundaries of our knowledge and to ponder what might lie beyond the visible universe. This collaborative effort opens the door to profound dialogues about the possibility of multiple universes, the true nature of space and time, and the ultimate destiny awaiting all existence. Exploring the boundaries of the universe showcases the importance of integrating both astrophysical and cosmological viewpoints to truly grasp these cosmic questions. Technological advancements have revolutionized our grasp of the universe's limits and behaviors. These breakthroughs transform once purely theoretical ideas into tangible subjects of exploration and experimentation. Powerful telescopes, for instance, have dramatically expanded our ability to observe distant galaxies, stars, and cosmic events by capturing light that has traveled billions of years to reach Earth. These observations grant insights into the early universe, offering clues about its expansion and the fundamental limits of space and time. Similarly, detectors placed deep underground enable the observation of rare particles originating from phenomena predicted by physics, such as interactions involving dark matter. These observations deepen our understanding of the fundamental building blocks of the cosmos, pushing the frontiers of what we once believed was knowable. Advances in particle collider technology also play a crucial role, allowing scientists to smash particles at unprecedented speeds. This recreation of conditions shortly after the Big Bang helps probe the fundamental forces and particles governing the universe and tests the boundaries of our current physical theories. Moreover, improvements in computational power have empowered scientists to create complex simulations that model physical interactions occurring under extreme conditions. These virtual experiments allow researchers to explore scenarios impossible to recreate in laboratories, such as the behavior of black holes or the intricate dance of space and time under the most intense forces. Each technological breakthrough opens new pathways for challenging existing theories and expanding the horizons of our cosmic understanding. Data analysis from space missions forms a critical pillar in our quest to comprehend the universe. Every spacecraft launched gathers vast amounts of data about celestial bodies, cosmic phenomena, and the conditions of outer space. These datasets include measurements of temperature, light composition, and gravitational effects, all of which are meticulously analyzed by scientists to yield meaningful insights. For example, missions studying distant planets reveal atmospheric conditions that help determine whether life might exist elsewhere. Observations of ancient stars offer clues about the universe's formation and evolution. Space missions also investigate fundamental questions such as the origins of cosmic rays, the properties of dark matter and dark energy, and the behavior of black holes. By analyzing these data, researchers construct models and simulations that predict how celestial phenomena might behave, leading to breakthroughs that push physics and astronomy forward. The collaborative nature of data analysis encourages knowledge sharing across the global scientific community. Different missions often focus on diverse aspects of the cosmos, and their combined datasets enrich our collective understanding, helping verify or challenge existing theories. Ultimately, data analysis from space missions transcends mere observation, acting as a transformative tool that turns raw information into profound discoveries about the cosmos and humanity's place within it. Computer simulations are another essential tool that helps scientists visualize and comprehend the vast and abstract regions of the universe that lie far beyond our direct reach. These simulations are intricate models designed to mimic real-world physical processes on a manageable scale. By programming algorithms that replicate the fundamental laws of physics, researchers can investigate complex phenomena that would otherwise be impossible to observe directly. Conditions in space can vary wildly, from dense star clusters to vast areas dominated by dark matter, an elusive substance believed to make up large portions of the universe, yet invisible to telescopes. Through simulations, scientists create virtual environments where they can experiment by adjusting variables such as the mass of celestial bodies or the rate at which different regions of space expand. This allows them to see how changes influence gravitational forces and the overall structure of the universe, providing invaluable insights into cosmic evolution and the nature of reality itself. Moreover, simulations offer a captivating window into some of the universe's most awe-inspiring phenomena, such as the formation of galaxies and the sprawling cosmic web. This cosmic web resembles a vast, tangled network, with nodes where countless galaxies gather, interconnected by filaments stretching across unimaginable distances. By visualizing how these immense structures evolve over billions of years, scientists gain profound insights into the processes that govern galaxy formation, their interactions, and the way they cluster together in groups and superclusters. These simulations serve as invaluable testing grounds for scientific theories. When the predictions generated by a simulation align closely with observations made through powerful telescopes and advanced instruments, it bolsters our confidence in those models and deepens our understanding of how the universe operates. However, when discrepancies arise, scientists are prompted to revisit and refine their theories, driving the continuous advancement of astrophysics. In this way, computer simulations transform the abstract and often intangible realm of the cosmos into vivid, tangible experiences. They turn intricate and complex astrophysical concepts into engaging visual stories, revealing the intricate relationships and subtle patterns that shape the environment of outer space. Particle physics plays an equally vital role in shaping our understanding of the universe's ultimate destiny. It offers essential clues about the fundamental forces and particles that govern cosmic behavior on the tiniest scales, shedding light on how these minuscule building blocks might influence the fate of the entire cosmos. To grasp this, we must first acknowledge that the universe is composed of matter and energy, interacting through four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. One of the most important concepts in particle physics is the Higgs boson, often described as the particle responsible for giving mass to other particles. The properties of the Higgs field, which permeates all space, may have profound implications for the universe's overall stability. If this stability were to be suddenly disrupted, it could trigger a catastrophic event known as vacuum instability. This hypothetical scenario suggests that a sudden shift in the Higgs field might set off a chain reaction of particle transformations, potentially obliterating the existing universe and replacing it with an entirely different state of reality. In addition, particle physics provides crucial insights into two of the universe's greatest mysteries: dark matter and dark energy. Dark matter, which interacts with ordinary matter only through gravity, is believed to play a fundamental role in shaping the structure of galaxies and galaxy clusters. Dark energy, on the other hand, is thought to drive the accelerating expansion of the universe. The delicate balance and interaction among these forces and components could determine a variety of possible futures. These range from a slow, endless cooling as the universe expands forever to a dramatic big crunch, where gravitational forces eventually pull everything back together. Some theoretical scenarios, such as the heat death of the universe, paint a picture of a far future where energy becomes evenly spread across space, stars burn out, galaxies drift apart, and all forms of life come to an end in an ever-cold, empty cosmos. Whether considering vacuum instability, the mysterious influence of dark energy, or the gradual depletion of usable energy, the ultimate fate of the universe traces back to the fundamental principles revealed by particle physics. Studying the smallest particles thus provides us with a valuable perspective on both the universe's grand evolution and its potential endings, illustrating that the journey toward the end is as intricate and complex as the cosmos itself. Interdisciplinary research plays a pivotal role in expanding our understanding of the universe's vast and mysterious boundaries. By integrating knowledge from various fields, physics, astronomy, mathematics, biology, and even philosophy, scientists approach questions from diverse angles, unlocking perspectives that might otherwise be overlooked by a single discipline. For example, astrophysicists investigate celestial phenomena, but by collaborating with mathematicians who specialize in complex algorithms, they can develop sophisticated models that simulate the behavior of galaxies or black holes on a cosmic scale. Biologists contribute by exploring the potential for life in extreme environments, sparking conversations about what forms life might take on distant planets or moons. This fusion of knowledge encourages innovative thinking and creative approaches. Take the exploration of dark matter and dark energy as an example. Physicists propose theories to explain these enigmatic components, while cosmologists and particle physicists ground these ideas in observable data, leading to more robust hypotheses about the universe's structure and fate. Interdisciplinary efforts also challenge existing paradigms. Philosophers offer critical reflections that help scientists reframe their questions and examine the foundational assumptions guiding their research. This synergy fosters a more holistic understanding of universal phenomena, driving not only theoretical progress but also technological innovations that open new frontiers for exploration. By merging expertise across disciplines, humanity deepens its knowledge of the universe and expands the very limits of what we can comprehend, bringing us ever closer to answering some of the most profound questions about existence and the cosmos. Scientific debates are a fundamental force driving progress at the edge of our understanding. The universe's boundaries are filled with mysteries that provoke deep questions and spirited discussions among researchers with diverse perspectives. These debates challenge established ideas, inspire fresh thinking, and push scientists to question their assumptions, design innovative experiments, and develop new theories. This collaborative process resembles a complex puzzle, where each participant contributes valuable pieces of knowledge and insight, leading to a richer understanding of intricate phenomena. Consider the ongoing debates about dark matter and dark energy, those elusive components that continue to puzzle scientists. Differing opinions about their nature and role fuel rigorous scrutiny and the proposal of new hypotheses. It is through this healthy contestation that better models emerge, models that can then be tested, refined, and improved. Furthermore, debates encourage advancements in technology and methodology, enabling researchers to gather data previously thought unattainable. In all scientific endeavors, this dynamic dialogue sharpens individual ideas and propels the entire field forward, fueling humanity's relentless quest to uncover the secrets of the universe. Moreover, when debates capture public attention, they engage a far broader audience in the scientific process than one might expect. This interaction not only raises awareness, but often leads to increased funding, opens doors to more research opportunities, and sparks greater enthusiasm for science education. Together, these effects can accelerate discoveries at the very edge of our understanding of the universe. Through constructive argument and collaboration, scientific debates create a fertile environment where breakthrough insights can flourish. These discussions illuminate the cosmos, expanding what we know about the vast unknown that stretches beyond our current grasp. When scientists share data across different disciplines, they unlock a treasure trove of knowledge that can spark unexpected discoveries and significant advancements. Each scientific field, whether it is biology, physics, or astronomy, operates with its own unique principles and methodologies. By making data accessible beyond these boundaries, Researchers gain the ability to view their work through fresh perspectives, revealing hidden patterns and connections that might otherwise go unnoticed. One of the most valuable lessons learned from this process is the power of collaboration. Diverse viewpoints fuel creativity as scientists pool their distinct expertise to tackle complex challenges. For example, understanding climate change demands cooperation among ecology, geology, and atmospheric sciences. By combining their data, these fields develop comprehensive models that consider multiple environmental factors, leading to more effective solutions. Interdisciplinary data sharing often raises new questions as well, uncovering unforeseen variables or phenomena that encourage scientists to widen their research scope. This can spark the creation of innovative hypotheses, such as how genetic research can inform medical practices, or how neuroscience findings might influence artificial intelligence development. Importantly, sharing data also promotes transparency and reproducibility in science. When studies are open and available to others, it fosters a culture of trust and accountability, essential for maintaining scientific integrity. Other researchers can replicate and verify findings, reinforcing the building blocks of knowledge that science depends upon. Ultimately, embracing interdisciplinary data sharing allows scientists not only to deepen their understanding of their own fields, but also to appreciate the intricate connections across various scientific realms. This collaborative spirit fuels progress and enriches our collective comprehension of the universe. The partnership between astronomers and physicists exemplifies this idea perfectly. Though these disciplines are distinct, they significantly overlap in their quest to understand the cosmos. Astronomers observe celestial phenomena, gathering data about everything from the structure of galaxies to the behavior of distant stars. Physicists, meanwhile, seek to explain the fundamental forces and principles behind these observations through theoretical frameworks and models. When these experts join forces, they blend observational data with theoretical insights to create a fuller, more nuanced picture of the universe. For instance, physicists develop theories about fundamental particles and forces, while astronomers test those theories by collecting data from telescopes and other instruments. If astronomers notice unexpected patterns in planetary motion or the universe's expansion, physicists may be prompted to revise long-held ideas about gravity or the nature of space and time. This dynamic relationship has led to groundbreaking discoveries. One of the most remarkable examples is the detection of gravitational waves, ripples in space and time caused by massive cosmic events. Physicists predicted their existence through Einstein's theory of general relativity decades before astronomers observed them directly. This collaborative effort not only confirmed a major prediction, but also opened a new window for exploring the universe, allowing us to detect phenomena that were once invisible. Interdisciplinary collaboration often inspires fresh questions and new lines of research. The mysteries of dark matter and dark energy illustrate this well. Astronomers observe the gravitational effects of these unseen components on galaxies and cosmic structures, while physicists explore theoretical models that might explain their nature. This back and forth encourages innovative theories and underscores how our understanding of the universe is constantly evolving through shared insights. The synergy between astronomers and physicists creates a richer dialogue about the cosmos that enabling more refined knowledge and fueling scientific breakthroughs. It is a vivid example of how the pursuit of knowledge thrives when diverse perspectives converge, ultimately deepening our grasp of the universe and our place within it. Looking ahead, several pioneering missions and technologies promise to push the boundaries of cosmic exploration. One of the most eagerly anticipated is the James Webb Space Telescope, designed to peer deeper into space and time than any instrument before it. With its powerful tools, it will study the birth of stars and galaxies, analyze distant exoplanets, and perhaps reveal clues about the building blocks of life elsewhere in the universe. In addition to this, the European Space Agency is preparing the Euclid mission aimed at unraveling the mysteries of dark energy and dark matter, two elusive components that make up a large portion of the cosmos but remain poorly understood. By mapping billions of galaxies, Euclid hopes to shed light on how these mysterious forces influence the structure and expansion of the universe. Together, these efforts exemplify the incredible progress driven by collaboration, debate, and data sharing. They hold the promise of transforming our understanding of the cosmos and revealing new secrets about the universe we call home. Furthermore, human exploration stands on the brink of a transformative leap with the Artemis program, an ambitious initiative designed to return astronauts to the moon. This mission is far more than a symbolic gesture. It aims to establish a long-term human presence on the lunar surface. By doing so, it will create a vital proving ground for the technologies that will enable future expeditions to Mars and beyond. Among the critical advancements being developed are life support systems that can sustain astronauts for extended periods, innovative habitat construction techniques to build safe and functional living spaces, and sustainable resource utilization methods that allow astronauts to use local materials on the moon. These breakthroughs are essential for missions venturing deeper into space, where resupply from Earth becomes impossible. On a more experimental front, a variety of robotic missions are scheduled to explore the outer planets and their moons, expanding our knowledge of the solar system's farthest reaches. NASA's Europa Clipper mission, for instance, is set to conduct detailed reconnaissance of Europa, one of Jupiter's icy moons. Scientists believe Europa hides a vast subsurface ocean beneath its frozen crust, making it one of the most promising places to search for conditions that could support life beyond Earth. In parallel with these explorations, groundbreaking technologies like space-based laser propulsion are being developed. This futuristic method uses intense beams of light to push spacecraft at speeds unattainable by traditional rockets, potentially opening new pathways for rapid, efficient travel across the solar system and even further into interstellar space. Together, these ventures symbolize humanity's relentless curiosity and determination to explore the unknown. Each mission brings us closer to answering some of the most profound questions about our origins and the universe itself. Alongside these physical journeys, the next generation of telescopes promises a revolutionary expansion in our cosmic vision. These powerful instruments will employ cutting-edge technologies that allow astronomers to capture light from the faintest and most distant objects in the cosmos. Imagine gazing at the night sky, not just through visible light, but also exploring the secrets hidden in infrared and ultraviolet wavelengths. This enhanced view will enable scientists to study celestial bodies typically obscured or too far away to observe with current technology. One of the most exciting frontiers opened by these telescopes is the detailed study of exoplanets, worlds orbiting stars beyond our solar system. Using advanced imaging and spectroscopic techniques, astronomers will detect and analyze the atmospheres of these distant planets, searching for signs that might indicate habitability or even life. This capability represents a monumental step forward in our quest to understand whether we are alone in the universe. Additionally, these new observatories will operate in large arrays, producing images with far greater detail than before. This improved resolution will allow us to study galaxies formed shortly after the Big Bang, piecing together the story of cosmic evolution over billions of years. The light reaching us from these ancient galaxies carries valuable information about their birth and the physical laws that shape them. Beyond uncovering the history of visible matter, these telescopes will also help map the elusive dark matter and dark energy, mysterious substances that compose most of the universe's mass energy content, but remain largely invisible and poorly understood. By observing their gravitational effects on galaxies and cosmic structures, scientists hope to unravel the forces driving the universe's accelerated expansion and gain insights into its ultimate destiny. Ultimately, this new generation of telescopes will not only extend our view to the furthest boundaries of the observable universe, but also deepen our understanding of the fundamental nature of matter, energy, and our place in the cosmic landscape. At the same time, quantum computation promises to revolutionize our grasp of the universe in ways that were once unimaginable. Leveraging the strange principles of quantum mechanics, quantum computers can tackle highly complex calculations far more efficiently than classical computers. This capability is especially crucial in astrophysics, where researchers grapple with phenomena involving intricate particle interactions and enormous volumes of data. One particularly exciting application lies in simulating quantum systems themselves. Traditional models often rely on approximations that limit accuracy, but quantum computers can directly model these systems with unprecedented precision, shedding new light on the fundamental forces and particles governing reality. By simulating extreme conditions, such as those found moments after the Big Bang or within the intense gravity of black holes, scientists can rigorously test and refine theories of physics. Moreover, quantum computing could dramatically enhance the analysis of massive datasets collected by telescopes and detectors. Fields like dark matter and dark energy research require sifting through vast observational information to identify subtle patterns and anomalies. Quantum algorithms have the potential to improve pattern recognition and uncover hidden signals that classical methods might miss, accelerating discoveries about the universe's most mysterious components. In this way, quantum computation and advanced observational technology together propel us into a new era of cosmic exploration and understanding, bringing humanity closer to unraveling the deepest mysteries of existence. Quantum communication holds the extraordinary promise of enabling secure data transmission across vast distances, connecting observatories separated by thousands of miles. This technology safeguards invaluable research findings from interception or tampering, ensuring that the most sensitive cosmic data remains protected. By establishing these secure channels, scientists worldwide could collaborate more effectively, sharing insights and discoveries in real time. This global network would bring together brilliant minds from diverse fields, united in their quest to unravel the mysteries of the cosmos. At the same time, advancements in quantum algorithms are opening new frontiers in our ability to tackle some of the most complex problems in gravitational physics and cosmology. Quantum computers, with their capacity to handle multiple dimensions and highly intricate mathematical structures, are uniquely suited to explore the fundamental nature of spacetime. These machines might enable researchers to probe theories that seek to unify the fundamental forces of nature, pushing the boundaries of what classical computers can achieve. As quantum computation continues to evolve, it stands to revolutionize our approach to understanding the universe, offering insights that remain beyond reach through traditional methods. Artificial intelligence and machine learning are also transforming cosmic research by vastly improving how we analyze the enormous volumes of data collected by telescope space missions. These technologies act as tireless assistants, processing millions of images and datasets at speeds far exceeding human capabilities. By detecting patterns and anomalies hidden within the data, AI can identify celestial objects ranging from distant galaxies to the faintest signs of potentially habitable exoplanets. One of the most exciting breakthroughs comes from applying machine learning to the detection of gravitational waves, subtle ripples in spacetime caused by cosmic collisions. These waves produce minute changes in data signals, and AI algorithms can rapidly filter out noise, highlighting significant events like the merging of black holes or neutron stars. Beyond detection, AI plays a crucial role in classifying various astronomical phenomena, such as different types of supernova or star categories. Machine learning models continuously improve their accuracy by learning from existing data, adapting quickly to the ever-changing discoveries made by astronomers. This adaptability is vital in the ongoing search for dark matter and dark energy, where AI assists researchers in modeling complex cosmic structures and their dynamics over immense scales of space and time. Simulating galaxy interactions under different conditions, scientists can better understand the invisible forces shaping our universe. Importantly, AI's impact extends beyond data analysis. It also enhances predictive modeling. This capability allows researchers to forecast cosmic events or estimate the likelihood of discovering new celestial bodies based on existing knowledge. Such foresight helps optimize the allocation of resources, guiding future observations and experiments toward the most promising targets. In essence, the fusion of artificial intelligence and machine learning with cosmic research accelerates discovery while offering deeper insights into the fundamental workings of the universe, fundamentally transforming how scientists explore the cosmos. Meanwhile, private sector involvement in space exploration is poised to revolutionize the way humanity pursues universal discoveries. Traditionally, space missions have been the realm of government-funded agencies, constrained by budget cycles and bureaucratic processes. The entrance of private companies introduces fresh energy, innovative technologies, and a more agile approach to space science. These companies often have access to substantial financial resources, enabling them to invest in cutting-edge technologies that might not be prioritized by government programs. This funding fuels the development of new spacecraft propulsion systems, advanced scientific instruments, and mission architectures that can dramatically enhance our ability to explore space. Furthermore, private industry's agility allows for rapid prototyping and deployment of missions, responding swiftly to new scientific opportunities or challenges. Unlike governmental programs, which can be slowed by administrative hurdles, private companies adapt quickly to shifting priorities, accelerating the pace of discovery. Partnerships between private firms and government agencies combine expertise and share risks, leading to more effective data collection, analysis, and dissemination. This collaborative culture encourages a global spirit of discovery where findings benefit scientists and the public worldwide. The commercialization of space travel also democratizes exploration, opening the door for a broader range of participants beyond traditional space agencies. This increased public engagement invites diverse perspectives and ideas, sparking innovation and expanding the possibilities for groundbreaking discoveries. When more voices contribute to the exploration of the cosmos, humanity's collective potential to understand the universe grows exponentially, promising a future filled with unprecedented scientific breakthroughs. Lastly, the private sector's role in space exploration extends far beyond activities near Earth. Companies are pushing the boundaries with missions targeting Mars and even further into the depths of space. They are also pioneering asteroid mining, a venture with the potential to unlock new materials and deepen our understanding of how our solar system has evolved over billions of years. These ambitious undertakings not only promise economic and technological rewards, but also enrich scientific knowledge, shaping how we perceive the universe itself. Private sector space exploration complements traditional scientific missions by injecting fresh ideas, innovative technologies, and new partnerships into the field. This dynamic collaboration accelerates discovery and expands human knowledge, weaving new threads into the vast tapestry of cosmic exploration. At the heart of this journey lies a profound question: are we alone in the cosmos? The search for extraterrestrial life is inseparably linked with our quest to understand the farthest edges of the universe. Scientists now look beyond the familiar territory of our solar system, reaching out toward distant stars and the countless exoplanets orbiting them. These worlds vary widely in size, composition, and distance from their stars, sparking questions about whether any of them could support life. With the advent of powerful astronomical instruments, we can observe galaxies so remote they were once thought unreachable. These observations help identify habitable zones, regions where temperatures and the presence of liquid water might resemble Earth's conditions, potentially nurturing life. Our expanding view of life's possibilities is influenced by discoveries on our own planet, where extremophiles, organisms thriving in Earth's most hostile environments, demonstrate that life can endure under conditions once considered uninhabitable. This revelation broadens the scope for where life might exist beyond Earth, encouraging scientists to consider diverse environments, from the icy moons orbiting gas giants to the thick atmospheres of distant, gas-rich planets. The story of cosmic evolution also informs this search. By studying how galaxies form and evolve at the universe's edges, we gain clues about how life might arise as a natural consequence of stellar and planetary formation. Stars create the conditions for complex chemical reactions that lead to the creation of organic molecules essential for life. Understanding these processes across the universe's immense timeline helps piece together where and how life might emerge. Moreover, the quest for extraterrestrial intelligence brings us to the cutting edge of technology, where powerful telescopes and listening devices scan the cosmos for signals from potential alien civilizations. This endeavor reflects a deep human desire not only to understand the universe scientifically, but also to find our place within it, perhaps connecting with other intelligent beings scattered across the cosmic expanse. As we push the frontiers of space exploration, insights gained from studying the edges of the universe profoundly impact our search for alien life. Scientists constantly probe phenomena beyond the reach of traditional observation. Gravitational waves, ripples in spacetime caused by massive cosmic collisions such as merging black holes or neutron stars, offer a new way to observe the universe. When detected, these waves reveal hidden details about violent cosmic events invisible to ordinary telescopes. Additionally, researchers are exploring the mysteries of dark matter and dark energy, which together make up a significant portion of the universe. Though invisible and not directly detected yet, scientists use advanced experiments like those conducted at the Large Hadron Collider and broad sky surveys to infer their properties. Understanding these dark components is crucial for grasping the universe's structure and its ongoing expansion. High-energy astrophysics opens another frontier. Space-based observatories capable of detecting X-rays and gamma rays enable us to study extreme cosmic phenomena, including intense gamma-ray bursts and enigmatic neutron stars. These observations provide vital insights into the fundamental forces shaping the cosmos. The pursuit of exoplanets remains a beacon of hope in this quest. Using methods such as transit measurements, where a planet passes in front of its star, or direct imaging, astronomers are discovering distant worlds that might harbor life-friendly conditions. Each new discovery expands our understanding of planetary systems, offering glimpses of possibilities far beyond our solar neighborhood and inspiring wonder about life's potential across the universe. Lastly, the relentless march of technological progress continues to expand the horizons of what we can observe and understand about the universe. Next-generation telescopes and advanced satellite missions are poised to revolutionize our view of the cosmos. As these powerful tools come online, they hold the promise of revealing phenomena that have so far eluded detection, challenging long-held assumptions and reshaping our cosmic perspective in profound ways. Together, these advancements are setting the stage for discoveries that could completely redefine our knowledge of the universe and its vast, mysterious expanse. In parallel, breakthroughs in propulsion technology stand to transform how we explore the cosmos itself. Imagine traveling to distant stars or even entire galaxies within a single human lifetime, rather than waiting for countless generations to pass. With advanced propulsion systems, regions of space once thought unreachable become accessible, enabling us to collect data and experience places previously confined to the realm of dreams. Some of the most exciting prospects involve technologies like ion propulsion, which uses streams of charged particles to generate thrust, or more speculative concepts such as nuclear thermal propulsion, which could dramatically increase travel efficiency compared to conventional chemical rockets. As these propulsion methods improve, spacecraft may carry heavier, more sophisticated scientific instruments, opening the door to revolutionary discoveries about planets, cosmic phenomena, and even the origins of the universe. Enhanced mobility would also greatly advance the search for extraterrestrial life. Missions to moons and planets within our solar system, such as Europa or Mars, both believed to have conditions suitable for life, could be executed more swiftly and effectively. This improved access would allow for more thorough sample collection and experimentation, greatly enriching our understanding of potential life beyond Earth. Furthermore, exploring the physics behind these advanced propulsion technologies could yield new insights into the fundamental laws governing reality. Theoretical concepts like warp drives, which propose faster-than-light travel, challenge our current understanding of space and time. Investigating these ideas could unveil new facets of relativity and quantum mechanics, pushing the boundaries of fundamental science. The evolution of propulsion technology will not only extend our reach into the universe, but also transform our scientific frameworks, expanding what we know and reshaping humanity's place within the cosmos. As we look forward, international collaboration in space exploration becomes increasingly essential. The immense scale of space and the complexity of its challenges mean no single nation can conquer these frontiers alone. Picture a global network of space agencies, researchers, and private companies uniting their expertise and technology to pursue bold missions together. Joint projects such as manned missions to Mars could see scientists from diverse countries sharing innovations in landing technologies, rover design, and sustainable life support systems. Such cooperation would not only maximize scientific achievements, but also promote peaceful relations and shared goals worldwide. These partnerships might also extend to astronomical observation, with multiple countries deploying observatories across the globe to monitor celestial events and gather data on phenomena like supernovae and exoplanets. This united effort ensures that the brightest minds from varied backgrounds collaborate to address some of the universe's most profound mysteries, from dark matter's elusive nature to the possibility of life elsewhere. Beyond observation, international teams could tackle the logistics of establishing human settlements on other planets or even asteroids, pooling resources to develop technologies necessary for sustainable living and resource utilization beyond Earth. Over time, this collaborative spirit could usher in a new era of space exploration where humanity collectively opens the path for future generations to journey beyond our home planet. Sharing the risks, rewards, and wonders of the cosmos together, we would embody a truly global venture into the unknown. At the same time, educational outreach plays a crucial role in inspiring young minds to engage with the universe's wonders. By providing interactive lessons, hands-on activities, and real-world applications, we invite children and teenagers to explore the vastness of space, the intricate behavior of celestial bodies, and the challenges of space travel. Introducing them to these concepts plants seeds of curiosity and amazement that can grow into lifelong passion. Programs that encourage building scale models of planets or simulating rocket launches make learning both fun and deeply meaningful. When students witness a model rocket soar or see a simulation of a rover navigating Mars's surface, abstract scientific ideas become tangible and real. This type of experiential learning fosters enthusiasm and motivates critical thinking about science and technology, preparing the next generation to push the boundaries of human knowledge even further. Moreover, storytelling holds a crucial place in how we share knowledge and inspire curiosity about space and science. When we hear stories about pioneering astronauts who dared to venture beyond our planet, groundbreaking scientists who unlocked the secrets of the universe, and thrilling discoveries that expand the frontiers of human understanding, our imaginations ignite. These personal tales of overcoming challenges in the relentless pursuit of knowledge resonate deeply, encouraging young people to see themselves as future innovators and explorers. Including diverse voices in these stories is equally important. When students from different backgrounds encounter narratives that reflect their own experiences and cultures, they can better envision their place in the ongoing journey of space exploration. Access to mentors and role models plays a vital role in this process. Programs that connect students with scientists and engineers offer more than just knowledge. They provide inspiration and confidence. These mentors show that anyone, regardless of background, has the potential to contribute meaningfully to the field of space. At its best, educational outreach creates a fertile environment where curiosity flourishes. By sparking enthusiasm for science, technology, engineering, and mathematics, and by nurturing a supportive community, we empower the next generation to dive into the mysteries of the cosmos. The universe is vast, filled with wonders and secrets waiting to be uncovered. With the right encouragement, today's youth will become tomorrow's pioneers, breaking new ground and expanding humanity's reach. Exploring the farthest edges of the universe is not just a scientific quest, it is a cultural journey that shapes how we see ourselves and the world. The desire to understand what lies beyond our familiar surroundings sparks creativity and imagination across many fields. When we gaze at distant galaxies and cosmic phenomena, we do more than observe. We reflect on our place in the grand scheme of existence. Questions about where we come from and where we are headed challenge us to rethink our values, philosophies, and even our relationships with each other. The discoveries made on the universe's fringes resonate deeply within the human spirit. The sight of stars and galaxies millions of light years away inspires stories of exploration and wonder, feeding our eternal search for knowledge. Artists, writers, and filmmakers often draw on these cosmic themes to explore profound questions about life, existence, and the possibility of beings beyond Earth. Science fiction thrives in this imaginative space, inviting audiences to picture future technologies and societies shaped by interstellar travel. Beyond storytelling, the breathtaking images captured by telescopes and space missions unite us. Stunning nebulae and the vast expanse of the cosmos remind us of our shared journey as a species. This shared vision can inspire a sense of unity and responsibility, urging us to care for our planet even as we reach for the stars. As researchers continue pushing the boundaries of knowledge, more people from diverse backgrounds are inspired to engage with science and technology. This growing curiosity fuels a culture that values inquiry, innovation, and critical thinking. The pursuit of answers at the edge of the universe can transform education itself, encouraging young minds to explore not only science and engineering, but also the arts. In this way, our cosmic exploration becomes a catalyst for broader cultural growth and transformation. Delving into the universe's boundaries also stirs deep philosophical questions that go beyond science. When we ask what lies beyond the edges of the universe, we confront the very nature of existence. Is what we see all there is, or is there something greater, an infinite realm beyond our understanding? These questions challenge how we perceive reality itself. The concept of time and space also comes into focus. If the universe has limits, what does that mean for time? Could time itself have a beginning and an end, shaping how we understand our place in this vast expanse? These ideas lead us to ponder cosmic origins. What sparked the universe into existence, and what does that say about cause and effect? Finally, considering the universe's boundaries invites reflection on human significance. Are we just tiny specks in a vast void, or does our consciousness hold a special place in a greater design? This question challenges us to explore the purpose of life itself. If the universe is infinite, do we hold deeper importance in understanding its mysteries? Or do we exist as part of a system indifferent to our presence? In grappling with these questions, the exploration of the cosmos becomes not only a scientific journey, but also a profound exploration of what it means to be human. Lastly, the investigation into the vast structure of the universe often stirs profound ethical questions as we seek answers about our cosmic home. How should we conduct ourselves in relation to the universe and to one another? Are there moral consequences tied to our actions, both here on Earth and potentially beyond? These questions become even more pressing as we entertain the possibility of life existing elsewhere in the cosmos. The philosophical reflections sparked by exploring the universe's boundaries push us to examine not only the stars, but also the very nature of our humanity. Gaining insight into the universe's limits deeply transforms how we view Earth and our place within the cosmic expanse. As we probe the universe's vastness, its immense age, and the fundamental laws that govern its behavior, we begin to grasp the delicate balance and fragility of our own planet. Earth is not merely a habitat. It is a rare oasis of life in a universe that is overwhelmingly vast and often hostile. Discovering that the universe stretches far beyond what our eyes can see, extending to distances that may be infinite, helps us understand how small a fraction of this immense cosmos our planet occupies. This awareness cultivates a profound sense of wonder and respect for the extraordinary conditions that allow life to flourish here. The Earth's atmosphere, the presence of liquid water, and the narrow range of temperatures suitable for life are far from ordinary. They are exceptional phenomena amid the extremes found throughout the universe. Furthermore, revelations about cosmic events, such as the life cycles of stars and spectacular phenomena like supernovae, underscore the interconnectedness of all things in the universe. We are reminded that the very atoms composing our bodies were born in the fiery hearts of ancient stars, linking us intimately to cosmic processes far beyond our planet. This perspective encourages humility, fostering a sense of shared existence and collective responsibility toward each other and the environment we inhabit. Understanding the universe's limits also forces us to confront urgent questions about the sustainability, the finite nature of Earth's resources. Recognizing that these resources are not unlimited urges us to adopt more thoughtful, conscientious approaches to how we live. This knowledge inspires efforts in conservation and innovation, pushing humanity to protect this fragile blue planet, which is vital not only for us, but perhaps for life itself, as we understand it in the universe. Far from diminishing our existence, a deeper understanding of the universe's boundaries elevates it. It calls us to become stewards of Earth while nurturing a greater appreciation for the extraordinary conditions that make life possible. Space exploration, one of humanity's most captivating pursuits, represents the ultimate quest for knowledge. It pushes the frontiers of what we know about ourselves and the universe that surrounds us. When we gaze up at the night sky, we do not just see distant stars, we see potential for discovery and connection with worlds beyond our own. This quest ignites a profound curiosity that has fueled human imagination for millennia, driving us to wonder whether we are alone in the cosmos and what mysteries lie beyond our home planet. By sending spacecraft to distant worlds and probing the farthest reaches of space, we transform abstract curiosity into concrete achievements. Each mission, from landing on the moon and exploring Mars to capturing stunning images of distant galaxies, fuels a collective story that intertwines science, engineering, and the indomitable human spirit of adventure. These journeys inspire generations to dream boldly and to reach for the stars, both literally and figuratively. Moreover, the images and discoveries unveiled through space exploration provoke awe and wonder, inviting people to question the fundamental aspects of existence, life, our place in the universe, and the future of humanity. These missions spark vital conversations about technology, cooperation, and the possibility of encountering life beyond Earth. Each venture serves as a poignant reminder of our shared hopes and challenges, fostering a sense of unity amid the immensity of the cosmos. Ultimately, space exploration is not only a scientific endeavor, but a reflection of human ambition, resilience, and creativity. It enriches our cultural fabric and instills hope for what lies ahead, suggesting that beyond our current understanding stretches an infinite horizon brimming with potential discoveries waiting to be unlocked. Discoveries about the edge of the universe could dramatically transform our understanding of existence and our role within it. Leading these breakthroughs may reveal the universe's structure and ultimate fate, clarifying whether it is finite or infinite. Such revelations could profoundly influence our philosophical and scientific reflections on life, compelling humanity to rethink its place in the grand cosmic story. Moreover, if humanity were to truly grasp the nature of dark energy and the ongoing expansion of the universe, it would open a doorway to predicting the far-reaching fate of galaxies, stars, and even our own solar system. Knowing whether the universe is accelerating its expansion or might one day contract would fundamentally shift our long-term focus. Such knowledge would drive the development of survival strategies and technological advancements aimed at securing humanity's continuity, potentially beyond Earth itself. This could mean preparing for life on other celestial bodies where human presence might endure despite cosmic changes. Discoveries at the universe's outermost edges hold the power to revolutionize our technological pursuits. Understanding the behavior of matter under extreme gravitational forces or the conditions surrounding black holes could ignite new innovations across various fields. Energy generation might evolve in ways we have yet to imagine. Materials science could develop substances stronger and lighter than anything now known, and computing could reach heights previously considered science fiction. These breakthroughs could empower humans to harness energy with unprecedented efficiency and unlock new methods of space travel, vastly extending our ability to explore the cosmos beyond our immediate neighborhood. Such revelations could do more than just inspire technology. They might also unify humanity with a shared sense of purpose. The awe and inspiration born from exploring the vast unknown could fuel a collective ambition to transcend earthly limits. This shared vision could promote international collaboration in scientific endeavors, creating a global community bonded by the quest to understand the universe. As we uncover more about the cosmos, the interconnectedness of all life may become increasingly evident, deepening our appreciation for the fragile balance of life on our planet amid the immensity of space. Ultimately, the journey to understand the universe's edge could redefine not only our technological and scientific ambitions, but also our very identity as a species. It would weave together our diverse experiences into a unifying narrative of exploration, discovery, and an insatiable thirst for knowledge that stretches beyond the stars. Unlocking the secrets of the cosmos has the potential to dramatically shape the path of scientific progress. Each groundbreaking discovery about phenomena like dark matter or the enigmatic nature of black holes sparks renewed curiosity and refocuses scientific inquiry. These revelations often raise new questions that demand attention, leading researchers to prioritize areas that may have once seemed peripheral. For example, gaining a clearer understanding of the universe's origins could shift the focus toward unraveling the fundamental laws that govern reality itself. Scientists might concentrate their efforts on particle physics or high-energy astrophysics, pushing experiments that probe deeper into the fabric of existence. Similarly, advances in studying exoplanets and their atmospheres could propel the search for extraterrestrial life, sparking innovations in astrobiology and planetary science that bring us closer to answering the age-old question of whether we are alone in the universe. Moreover, cosmic discoveries often act as powerful catalysts for technological progress. The tools and innovations initially designed for exploring the far reaches of space frequently find unexpected applications here on Earth, transforming industries and everyday life. This dynamic exchange between cosmic exploration and terrestrial technology sparks enthusiasm that fuels funding and resource allocation toward a variety of fields, including engineering, data science, and environmental research. The thrill of confirming scientific theories or unveiling new cosmic phenomena breathes life not only into astronomy, but also invigorates a broad spectrum of scientific disciplines. This collective excitement drives exploration forward, feeding humanity's insatiable hunger to expand knowledge and push boundaries. As we unravel the mysteries of the cosmos, we gain a richer and broader perspective of our place in the universe. These revelations challenge us to reconsider which questions truly matter and help shape the technologies and strategies best suited to fuel our ongoing quest for understanding. Each answer we uncover nudges open the door to fresh questions, crafting a constantly shifting landscape of scientific priorities that evolve alongside our growing cosmic awareness. Throughout history, our understanding of the universe's limits has profoundly influenced the way we pursue cosmic phenomena. Ancient civilizations, for example, often viewed the cosmos as a fixed, Earth-centered system, imagining that the stars and planets moved in perfect circles around our home planet. This geocentric view placed humanity at the universe's heart, but also limited the scope of what could be imagined or known. As observational instruments advanced and thinkers like Nicolaus Copernicus introduced the heliocentric model, where planets orbit the sun, our conceptual universe expanded dramatically, moving us away from Earth-centric assumptions. Fast forward to the 20th century, and the invention of the telescope revealed that our Milky Way galaxy was just one among countless others, fundamentally transforming our sense of cosmic scale. Edwin Hubble's discovery of the expanding universe shattered the notion of a static cosmos and introduced the idea that the universe itself is dynamic and ever-changing. This insight set the stage for the Big Bang Theory, which posits that the universe originated from an unimaginably hot and dense singularity. Today, these foundational discoveries continue to underpin research into dark matter and dark energy, the mysterious forces propelling the universe's expansion, and highlight how scientific limits are less about fixed borders and more about evolving concepts shaped by ongoing discovery. Modern researchers harness advanced technologies, including powerful telescopes and particle accelerators, to probe the universe's farthest reaches. Their goal is to decode its composition and uncover its ultimate fate, carrying forward the legacy of past breakthroughs. Historical interpretations remind us that every scientific leap deepens our appreciation of the cosmos and teaches us to remain open to new revelations that may forever alter our understanding of universal boundaries. Humanity's journey to explore cosmic frontiers has also woven itself into rich cultural narratives that reflect our collective hopes, fears, and aspirations. Where once space was the realm of myth and wonder, it now serves as a stage for stories that explore our place in the cosmos. Ancient civilizations crafted myths to explain celestial events, while modern science fiction delves into themes of technological advancement and extraterrestrial contact. These narratives shape how we imagine the universe and our role within it. One powerful recurring story is that of humanity as intrepid explorers. As technology advanced to allow journeys beyond Earth, tales of brave astronauts venturing into the unknown emerged, highlighting both awe-inspiring discoveries and the chilling uncertainties of space travel. Films and literature often portray protagonists grappling with isolation, the fragility of life in a hostile environment, and the search for meaning amid the vast, cold expanse of the cosmos. These themes strike a deep chord within us, mirroring our fears about the unknown alongside an unyielding drive to explore. Another compelling thread in cosmic storytelling is the search for extraterrestrial life. This quest has sparked countless narratives pondering what it would mean to discover intelligent beings beyond Earth. Such stories question humanity's uniqueness and speculate on how we might interact with alien civilizations. Encounters with other life forms often force us to rethink concepts of life, ethics, and civilization, inviting us to reflect on our own humanity and how we would respond to the complexities and challenges such contact might bring. The exploration of cosmic boundaries also inspires philosophical reflections on existence and destiny. The vastness of space provokes profound questions about humanity's role in the universe, sparking debates about fate, free will, and the forces shaping our lives. These ideas find expression in literature and film, where characters confront their limitations and the immense powers governing the cosmos. Such narratives encourage us to ponder our place in the universe, the legacies we wish to leave, and the meaning behind our relentless push into the unknown. As humanity embarks on robotic missions to distant planets or prepares for human expeditions to Mars, these cultural stories continue to evolve. They inspire new generations not only to look beyond our world, but to contemplate what it means to be human within a universe still shrouded in mystery. Each venture into space becomes a mirror, reflecting our shared consciousness and an exploration of the intertwined destiny between humankind and the cosmos. With every scientific breakthrough, individual worldviews about the cosmos transform. Early perspectives, often shaped by myths, legends, and religious beliefs, attributed celestial events to divine forces, offering comfort and explanations for phenomena like seasons and star movements. As science advanced, the heliocentric model upended Earth-centered views and sparked a wave of questioning about humanity's cosmic significance. Discoveries such as the laws of gravity and the nature of light revealed rational explanations for many mysteries, further shifting public understanding. Deeper insights from astronomy, cosmology, and physics have expanded our awareness of the universe's staggering scale and complexity. The possibility of life beyond Earth, once relegated to the realm of speculation, now seems increasingly plausible. These shifts have transformed feelings of isolation into a recognition of our part in an immense, interconnected cosmic tapestry. In this light, humanity no longer stands as the center of all things, but as one thread woven into the vast fabric of the universe, inspiring wonder, curiosity, and a continual drive to explore. Moreover, as scientific advancements gradually unveil the majestic stories of the cosmos, from the birth of stars to the evolution of galaxies, and even the fundamental laws that govern all matter, our sense of human significance undergoes a profound transformation. With every new insight into concepts like the Big Bang and the relentless expansion of the universe, individuals face a complex mix of feelings. On one hand, there is a humbling awareness of our smallness in the vast cosmic expanse. On the other hand, there is a remarkable realization of the deep connection we share with everything beyond our immediate experience. This constantly evolving worldview does more than reshape how we see the universe. It also influences our emotional and philosophical outlooks. As scientific literacy spreads widely, more people begin to favor evidence-based explanations over rigid adherence to tradition or dogma. This cultural shift sparks curiosity and a thirst for exploration, nurturing an inquisitive mindset that values discovery and understanding. While some might find this expanding perspective daunting or unsettling, many others find it a source of awe and wonder. It encourages a deeper appreciation for the intricate, delicate workings of the cosmos and our unique place within it. As humanity's knowledge grows, so does the complexity and nuance of our collective worldview. Each new discovery is like adding another piece to an enormous, ever-changing puzzle. People continually reconstruct their understanding of existence, weaving together scientific insights with personal meaning and purpose. The quest for universal knowledge shapes not only how we view the universe, but also how we consider our ethical responsibilities here on Earth. Exploring the vast universe often arises from a fundamental desire to understand our origins, the nature of existence itself, and the possibility of life beyond our planet. This journey compels us to reflect on how these newfound insights affect not only our self-understanding, but also the moral principles guiding our interactions with one another and the environment. For example, advancements in space exploration have led to new technologies that benefit humanity in many ways. However, these innovations also raise important ethical questions. Who should have access to these transformative technologies? How do we ensure they are distributed fairly so that inequalities do not deepen and only a privileged few reap the benefits? Balancing the excitement of discovery with the imperative of justice becomes crucial. In addition, contemplating the potential existence of extraterrestrial life or the possibility of colonizing other worlds brings forth entirely new ethical dilemmas. If we were to find microbial life on another planet, what responsibilities would we have toward these life forms? Could we prioritize human exploration without causing harm to alien ecosystems? Addressing such questions requires a carefully developed ethical framework that respects life in all its forms, urging us to act with foresight and care. Moreover, as we uncover universal truths, we must also reconcile them with the diverse cultural beliefs and values that exist across our planet. The pursuit of knowledge can sometimes challenge traditional worldviews, leading to ethical conflicts that demand open dialogue and mutual respect. Ideally, the knowledge we gain should encourage collaboration and inclusivity, rather than division and strife. The quest for universal understanding serves as a catalyst for deep reflection on our ethical responsibilities, not only as explorers of the cosmos, but also as stewards of our planet and its rich diversity of life. This ongoing journey calls for a commitment to thoughtful engagement with the implications of our discoveries. It invites us to envision a future where knowledge uplifts all humanity rather than creating new divides. Humans possess an innate curiosity about the unknown, a natural drive to explore and understand the world around them. Since ancient times, our ancestors gazed at the stars, wondering about the mysteries beyond Earth's boundaries. This intrinsic desire to seek knowledge shapes cultures, fuels scientific inquiry, and inspires continuous innovation. The unknown, particularly the vastness of space, symbolizes the ultimate frontier, an immense realm filled with secrets that could radically expand our understanding of existence. Questions like whether we are alone in the universe or what the fundamental nature of reality is push us to seek answers that remind us of our place in the cosmos. By exploring beyond our world, we connect with the grand narrative of life itself. Every discovery, whether identifying distant galaxies or understanding cosmic phenomena such as black holes, enriches our worldview and ignites a shared sense of adventure. As we learn more about the universe, we also uncover deeper insights about ourselves, our history, and our potential futures. This delicate balance of curiosity, discovery, and self-reflection motivates us to gaze into the depths of space, yearning to understand what lies just beyond our reach. Scientists navigating these cosmic mysteries rely on a multifaceted approach that blends creativity, rigorous experimentation, and collaborative inquiry. They begin by recognizing the limits of current knowledge, knowing that each answer often leads to new questions rather than final conclusions. This mindset propels their quest for understanding forward. One essential method is the formulation of hypotheses, educated guesses grounded in existing theories and observations. These hypotheses guide researchers as they design experiments or observations to gather new data. Whether through telescopes probing distant galaxies or particle colliders uncovering the hidden nature of matter, each experiment represents a step forward. Even when results are unexpected or contradict previous theories, They provide critical insights that refine our understanding of the universe. Moreover, scientists continually embrace the rapid pace of technological advancement to push the frontiers of their exploration far beyond what was once conceivable. Innovations such as enhanced sensory instruments and sophisticated computational models now open doors to realms that were previously locked away from human reach. Take, for example, the emergence of powerful space telescopes, which have revolutionized our ability to peer into distant corners of the cosmos. These instruments allow us to observe exoplanets orbiting other stars and study cosmic phenomena in exquisite detail, illuminating regions of the universe that were once shrouded in darkness and mystery. Collaboration stands as another essential pillar in modern scientific progress. Researchers from a wide array of disciplines come together, fostering rich interdisciplinary conversations that deepen their collective insight. This spirit of cooperation encourages the free exchange of knowledge, often sparking groundbreaking discoveries by blending ideas from different scientific fields. Such cross-pollination enriches the understanding of complex problems, weaving connections that can elevate entire branches of science to new heights. At the core of this endeavor is a mindset defined by open-mindedness and adaptability. Scientists understand that the universe frequently behaves in ways that defy initial expectations. The hallmark of scientific progress lies in the readiness to revise or even overturn theories when confronted with fresh evidence. Embracing uncertainty not as a hindrance, but as a vital ingredient in the quest for knowledge, researchers persistently push the limits of what we know, transforming questions into revelations that inspire generations to come. Cosmologists, in particular, face the profound challenge of communicating the vastness and complexity of the universe's fabric to the public. To bridge the gap between abstract scientific concepts and everyday understanding, they employ various effective methods. Analogies serve as a primary tool. By comparing the expanding universe to something tangible, like a balloon inflating or a stretching fabric, they translate the difficult ideas of space and time into relatable imagery. Visualization further amplifies this effort. Through detailed illustrations, computer simulations, and immersive virtual reality experiences, cosmologists conjure vivid representations of cosmic events. These visuals offer a window into phenomena such as the bending of space or the vast distribution of galaxies, making it possible for audiences to grasp concepts that defy simple verbal explanation. Storytelling plays a critical role in bringing the cosmos to life. By weaving narratives about the life cycles of stars, the birth and growth of galaxies, or the enigmatic nature of dark matter, cosmologists engage both the hearts and minds of their audiences. These stories distill the essence of complex cosmic processes into experiences that resonate emotionally and intellectually, inspiring curiosity and wonder. Public lectures, documentaries, and educational outreach programs further democratize access to these ideas. Through these platforms, cosmologists present their discoveries in accessible formats, inviting questions and fostering dialogue that enhances understanding. Collaborations with artists and communicators help transform dense scientific jargon into appealing, comprehensible content. This partnership between science and creativity boosts the clarity and appeal of complex ideas, broadening their reach and impact. Through this blend of analogy, visualization, storytelling, public engagement, and artistic collaboration, cosmologists effectively illuminate the abstract and often intangible concepts surrounding the universe's boundaries. They invite everyone to join in the exploration of the cosmos, transforming the universe's mysteries into shared human adventure. The question of where the universe ends, or whether it even has an edge at all, continues to captivate and challenge scientists. Imagine standing at the metaphorical brink of a vast, uncharted ocean filled with infinite possibilities. This enigmatic edge pushes researchers to ponder not only what lies beyond our observable universe, but also the very nature of these boundaries. Are they physical limits, or something more elusive? The mystery of the universe's edges inspires scientists to think beyond conventional wisdom. Some propose that the universe might be infinite, perpetually expanding like a balloon being inflated without end. Others suggest it could be curved back onto itself, resembling a sphere with no true edge. Each theory demands bold, innovative thinking and the development of new concepts which scientists rigorously test against observational data. This cosmic enigma encourages vibrant interdisciplinary collaboration. Astrophysicists, mathematicians, computer scientists, and philosophers all bring their unique perspectives to the table. Together, they explore profound questions about dark matter and dark energy, enigmatic substances that seem to govern the universe's structure and expansion. These mysteries illustrate how the unknown compels diverse approaches and novel experimental designs. The obscurity surrounding the universe's boundaries acts as a fertile canvas for scientific creativity. It prompts researchers to move beyond established frameworks and consider radical ideas, such as alternate dimensions or the existence of a multiverse, a vast collection of multiple, perhaps infinite universes. Each question deepens our cosmic understanding and propels humanity forward in the grand quest to comprehend existence itself. Historically, the pursuit of the universe's edges has profoundly influenced the course of science. From ancient philosophers gazing at the night sky and speculating about celestial bodies, to modern astronomers mapping galaxies billions of light years away, this quest has fueled humanity's desire to understand the fundamental nature of reality. During the Age of Exploration, the desire to chart Earth's boundaries spurred advances in astronomy. Navigators relied on the stars for safe passage, leading to the invention of telescopes that unlocked unprecedented views of the heavens. Galileo's observations in the early 17th century, revealing moons orbiting Jupiter, challenged long-held beliefs that all celestial bodies circled Earth. This pivotal discovery expanded human perspective from a geocentric to a heliocentric view, laying the groundwork for modern cosmology. As humanity's cosmic horizons broadened, the concept of infinity began to take shape. The realization that the night sky is populated by countless stars, many far beyond immediate reach, inspired thinkers like Isaac Newton. His laws of motion and universal gravitation not only explained earthly phenomena, but also unveiled the predictable mechanics of celestial bodies, setting the stage for centuries of cosmic exploration. The 20th century marked another giant leap forward. Powerful telescopes capable of detecting distant galaxies revealed that the universe is not static, but constantly expanding. Edwin Hubble's observations demonstrated that galaxies are receding from each other, a discovery that reshaped our understanding of cosmic history. This insight led to the formulation of the Big Bang theory, which posits that the universe originated from an incredibly dense and hot state, fundamentally transforming our view of origins and the flow of time. Through centuries of inquiry, technological innovation, and collaborative spirit, the pursuit to understand the universe's edge continues to drive humanity deeper into the cosmic unknown, turning mysteries into discoveries that expand our place in the cosmos. Moreover, the quest to understand the universe has always been tightly intertwined with technological progress. Every major breakthrough in our grasp of the cosmos has come hand in hand with improvements in the tools we use to observe and measure it. From the early days of radio telescopes picking up faint cosmic radiation signals to modern space probes journeying into the most remote corners of our solar system, each innovation reflects a deep human desire to see beyond what our eyes can perceive. This dynamic dance between pure scientific curiosity and practical invention highlights how theory and application continuously feed off each other. As humanity pushes forward to explore the edges of the universe, this relentless drive reveals not only our insatiable curiosity, but also a persistent hunger for knowledge. Every scientific discovery becomes a stepping stone that lifts the veil on the cosmos, while also shining a light on our own place within the grand scheme of things. Even as researchers extend the boundaries of what we can observe, the quest remains alive and vital, woven into the very fabric of human understanding. This pursuit shapes more than just facts and figures. It deeply influences our psychological and emotional landscape. Our innate curiosity about the cosmos sparks feelings of wonder and awe, encouraging creativity and innovation. It fosters a spirit of exploration that is fundamentally woven into human nature. Whether we uncover a distant galaxy or decode the behavior of cosmic phenomena, the experience often mixes fascination with humility. The vastness of space puts our personal lives and challenges into perspective, underscoring both our seeming insignificance and our unique place in the universe's vast tapestry. This duality can evoke a profound sense of connection to something greater, inspiring appreciation for life and the natural world. Yet the quest to comprehend the universe also stirs existential questions. As we ponder where we come from and where we might be headed, some may feel uncertainty or anxiety about the future. Ideas like the possibility of extraterrestrial life, the fate of our planet, or the ultimate end of the universe provoke a wide spectrum of emotions, from fear to hope. Beyond the individual experience, the vast and complex nature of space research creates a powerful sense of community among those who share in this journey. Scientists, enthusiasts, and ordinary people bond through collaboration, just driven by shared exploration that transcends geography and culture. This collective effort offers a deep sense of purpose as we build a common understanding of the cosmos. Ultimately, the psychological impact of our cosmic quest is complex and multifaceted. It fuels imagination, challenges intellect, and pushes us toward profound reflections on existence. Confronting the mysteries of the universe means confronting the depths of the human experience itself. Artists and writers play an essential role in this process by translating scientific ideas into stories and visuals that resonate with the broader public. They transform abstract, complex theories of physics, astronomy, and cosmology into narratives that spark curiosity and wonder. When an author imagines traveling through space or living on another world, they don't just entertain, they invite readers to engage with real scientific concepts. Similarly, visual art captures the grandeur of the cosmos in ways that engage the senses and emotions. Stunning images of galaxies, nebulae, and celestial events move viewers beyond cold facts, inspiring deeper emotional connections and reflection on our place in the universe. Stories infused with scientific themes often explore philosophical questions about humanity, reality, and the ethics of space exploration. By doing so, artists and writers encourage ongoing conversations about what it means to be human and how society should respond to scientific progress. This fusion of art and science expands our understanding, making the universe's mysteries more approachable and igniting a shared spark of wonder. Throughout history, humans have gazed at the night sky and tried to make sense of the cosmos. Ancient myths and legends often captured celestial phenomena in ways that reflected the environment, beliefs, and hopes of their cultures. Many civilizations crafted stories around star constellations, attributing their shapes to heroes, animals, or gods. These narratives helped explain the seemingly chaotic cosmos and offered frameworks for understanding natural cycles like seasons and eclipses. Intriguingly, modern astronomical discoveries echo many of these ancient themes. Take, for example, the myth of the celestial sea represented by the Milky Way. Ancient peoples imagined this glowing band as a river or pathway to the afterlife. Today, we know it as a vast spiral galaxy containing billions of stars, many likely hosting planets that might harbor life. This connection between myth and science highlights a shared human fascination with exploration and the search for immortality through knowledge. Creation stories from various cultures often feature dramatic cosmic battles or the emergence of order from chaos, paralleling the Big Bang Theory. Just as these myths describe the universe being born from a primordial explosion or conflict, modern science explains that the cosmos began as an extremely dense point and has been expanding ever since. This parallel shows how ancient narratives resonate with contemporary scientific insights, transforming chaos into order. Legends about cosmic giants or beings shaping the world also find a counterpart in modern astrophysics. These mythical figures often symbolize natural forces like creation or destruction. Today, researchers study phenomena such as supernovae and black holes, which have the power to reshape galaxies and influence the birth of stars and planets. The link between mythological giants and these cosmic forces reveals humanity's enduring awe toward the universe's immense and sometimes unfathomable power. This rich tapestry of myths and scientific discovery underscores humanity's ongoing quest to understand its place in the cosmos. As we reveal deeper truths about the universe, it becomes clear that these timeless stories still resonate, bridging ancient wisdom with modern knowledge. The universe continues to captivate both the imaginative hearts of our ancestors and the inquisitive minds of today's explorers. Exploring the universe's edge invites us to grapple with profound questions about existence and reality. Standing at the boundary of the known cosmos, where the vastness stretches infinitely, encourages deep reflection on what it means to be part of something so immense and largely unexplored. Scientists working at this frontier wrestle with ideas of beginnings and endings. How did the universe come into existence? Does it have a boundary, or is it an endless expanse beyond our comprehension? These questions tap into a fundamental human desire to understand the origins of everything. The immense scale of the universe and the mysteries at its edges challenge our sense of significance in an almost unimaginable context. Moreover, pondering the limits of the universe leads to questions about time and what might lie beyond our perception. If the cosmos has an edge, is there something beyond it? This intersection of time and space pushes us to rethink eternity and the fleeting nature of our own existence. The expanding universe evokes reflections on isolation and connection as galaxies drift apart. What does the future hold for our celestial neighborhood in an ever-growing cosmos? Might we eventually be left alone in the void? These thoughts foster a sense of urgency about how we live and act, both individually and collectively. Studying the universe's edge is not just about cataloging stars and galaxies. It is about confronting essential questions of purpose, existence, and what it means to be human in a universe that is both magnificent and indifferent. Each new discovery broadens our scientific horizons and deepens our self-understanding, placing us within the grand cosmic tapestry. Scientific paradigms, frameworks through which we interpret observations, shape how we understand the universe and our place within it. When a paradigm shifts, it changes not only science, but also culture, natural perceptions, and philosophy. For example, the heliocentric model that placed the sun at the center of the solar system revolutionized humanity's view of itself. We were no longer the center of everything, but one planet orbiting a star in vast space. This realization sparked the scientific revolution, which led to leaps in navigation, exploration, and understanding gravity, expanding the universe in our collective imagination. As new discoveries arise, such as the expanding universe or the existence of dark matter and dark energy, they continually redefine the boundaries of our knowledge. Each insight challenges old ideas, forcing society to reconsider the universe's size, makeup, and ultimate fate. Realizing that the cosmos extends far beyond what we can see hints at hidden richness beyond our experience, inspiring both scientists and everyday people to ponder deeper questions. These shifts also have practical consequences. Advances in physics and space exploration drive new technologies that affect industries, education, and policy. As human knowledge grows, so does our capacity to innovate and address pressing challenges like climate change and resource management. Thus, the ongoing interplay between evolving scientific understanding and society's worldview shapes not only how we perceive our cosmic neighborhood, but also how we act on Earth.